Hi.
Good evening.
Good evening. Good morning there. Hello, good morning.
Good morning. Yeah.
Yeah. Anyway, what about the time there? Morning time.
Yeah, 7:57.
Okay. Good evening, Kalyan sir. Good evening. Good evening. Okay, let us start the.
Yeah.
Yeah. Today the third. Good evening, good morning, good evening, good afternoon to all. Today the third day of the workshop on international workshop on distribution theory and its applications. And here today we have two eminent speakers, Professor Ashokan Variath from Newfoundland University, Canada, and Professor K.K. Jose from M.G. Mahatma Gandhi University, Kolkata, India. First of all, before our students are some, I think Krishnaveni is there here in the group to introduce our speaker and invite him for the talk. Now it is the time. Without wasting time, please go ahead.
Yes, sir.
Let us go ahead. Yeah.
A very warm greetings to each and everyone present virtually over here. It is my privilege to welcome Mr. Ashokan Mulayath Variath, Associate Professor of Statistics of the Department of Mathematics and Statistics at the Memorial University of Newfoundland, Canada, to speak on the topic Variable Selection Approaches in Generalized Linear Models. Professor Ashokan Variath has worked as a faculty member at SQC and OR Division of Indian Statistical Institute. He had obtained his PhD in statistics from University of Waterloo in 2006 and then moved to Texas A&M University as postdoc. He joined Memorial University as Assistant Professor of Statistics in 2008 and currently works as the Associate Professor of Statistics there. His main research interests are industrial statistics, design of experiments, survival analysis, and longitudinal studies. With great pleasure, I invite you, Professor, for your presentation. Over to you, sir.
Yeah, thank you. So, good evening or good morning to everyone. So, it is early morning here, 8 o'clock here. So, I have a pleasure in participating in this workshop and thanks for the University of Kerala and Dr. Sadish Kumar for inviting me for this international workshop. And nowadays it's very easy because the COVID gives some idea about easy communications through this Google Meet or Zoom. So that very easy to communicate with the many people around the world. So I'm taking that opportunity here because there's no need for me to come over there. So I have a good association with the University of Kerala. I used to participate in these workshops and conferences for the last 8 to 9 years. So, and it is a good opportunity and good thing Kerala, University of Kerala is doing on disseminating the knowledge and participating many around the world to get information and discussion to how to improve on the research and the teaching and everything. So without much delay, I will get into my topic today. And as the introduction in the mention, I studied in Kerala and Kolkata as part of my MSc and postgraduate diploma in quality control and operation research, and I joined the SI for work there as more than 10 years before I moved to Canada to do my PhD. And okay, so without much delay, I will go to my topic. Where to screen? Where is the sharing one?
There is an upward arrow in the bottom. You can just click on there.
Yeah, that is your
And,
entire screen
your
or
entire-
window.
Your entire screen. Your entire screen.
Yeah, then
Then you can click on that pop-up box there. There's a box.
okay.
So the share button is active.
Yeah.
Oh yeah, coming.
Yeah, I almost used the
The
Zoom one, that is why.
Oh yeah. We know. Yeah.
What is coming there?
So you can go to the slides.
Can you see the slide now?
Yeah. Now it is visible. Yeah, it is fine. Yeah. Now it is full screen. Okay. Fine. Yeah. Now it is fine. No problem. I think so.
Okay, no, just I'm trying to go. The full screen is possible or
Yeah.
not.
Better. And then
Edit. Is it fine now?
it is fine now. No problem. It is fine.
But I cannot go to this full screen here. 1 minute.
There is
No, this one is.
since it is Apple, you can make it in the. There is a green or left top green button is there. Left top.
Yeah, because maybe I opened it in the web. That's the issue. Okay.
Yeah, that screen you can make it full screen because there's a left top green button. 3 small buttons are there in left top of that.
Yeah.
That's fine. Now, not make, left upper top left top.
Okay.
There is a red, yellow, green. That green you can make it. Click on that green. Oh.
No, it's not coming there.
Yeah. No. Once again. Yeah. Or command L. Make it full screen.
Command?
L.
L.
Yeah. Is it L? Just usually we do in that. Click on that small button. Green, sir. Yeah, not green. In the left top, there is a three small circles: red, yellow, green. Then click on that green circle, left top corner.
On my PDF file or?
Yeah, on that file itself. That PDF file. On that PDF file. The left corner.
Left corner, no.
Left corner. That is usually in Apple.
Yeah.
Yeah. There is the left corner. There is a small, three small circles, red, yellow, green are there.
Yeah, I understand. I could not find that one. Anyway.
Next, yeah, you can go to your cursor. You please go to.
Is it going now? Side is moving?
Yeah, it is fine. It is fine. No problem.
Is it okay? Yeah, I'll go with this then. I don't want to.
Yeah. It's okay. No problem.
Okay. Okay, so.
Okay. It is fine.
Okay,
if you need it, you can do. Yeah.
Yeah. Without much delay, I will start. Okay, so I will go into two sessions. I think 45 minutes or 50 minutes. I'll stop for 5 minutes or 10 minutes. Then you'll come back again. Okay. So, so my talk today is on variable selection in generalized linear model. So in this talk, I'll give a basic introduction to the variable selection, why we need to do this variable selection in the general scenario, and what are the traditional variable selection methods are available. So that is a commonly used one. So then we'll go a little bit on penalized likelihood-based variable selection. Then I'll discuss one example, and if time permits, we'll talk about a little bit on how we can do it in R software. Then I'll summarize this talk. Okay. So one of the most commonly used methods in statistical analysis is the regression modeling. So why do you want to do that? So in the regression modeling, we have a response variable y, and most of the time we normally do the statistical analysis based on this y. But in regression analysis, we have a set of other variables, so which are dependent on this response, and we model the relationship between the response variable and the other independent variable, what you otherwise we call the covariates. So it is a mathematical description of the process in terms of associated variables. So we have a main interest variable is there, and we have set of associated variables, and we try to make a mathematical description of this relationship. Okay, that means the value of the one variable, that is the one we're interested, is dependent on the several levels of the other variables. Okay, so maybe because, for example, a simple case like we normally have a blood pressure or any response variable, and we can talk about in terms of how it is related to the male and female. Okay, so that is a categorical variable in the covariates. Then we can find out how this is depending on the sex of the individual. So before we fitting a model, so we know the y, and we have a lot of explanatory variables are available, and we always find out better to dependency of this. So how this response variable and explanatory variables are related or dependent on scientifically. So scientifically, in the sense, so we can always find out some relationship from the data when you plot or anything, but we need to know exactly what is the scientific relationship is there or not. So if there is no scientific relationship, then there's no point in fitting a model, because model may give you a good relationship or based on the data, but it is very difficult sometimes to explain that scientifically. Okay, so for example, if you look at a relationship which is no relation at all in scientifically, but a data can give that. For example, if you look at the response variable as the marks obtained by the students and what the number of or how much food they're eating every day. So sometimes we find a relationship, but we cannot see that relationship is going to play a big role in that. So scientifically, very difficult to justify that. So whenever we fit the regression modeling, so the scientific knowledge is very important, or from where the data is coming, how this the data is generated, either in a scientific relationship is there, then only we need to do. So as a statistician, when we fit this model, it's always better to get the advice from the person or the organization or the process from which the data we collected, have a discussion and identify the variable they think it is meaningful. So once the relationship is scientifically justified, sorry, then you can use our tools available, especially simplest one is the scatter diagram, to understand the nature of relationship and fit appropriate model. So once you know, okay, this y and the one explanatory variable x1 as scientifically meaningful, the relationship, then we can plot and see what type of relationship. They have a linear or a curve or curvature, or what type of things are there. So we can identify what type of modeling we use. Okay, so we may use a y and x1 or y and x1 square, the quadratic form, or cubic form, or combined form. So we can identify that using a proper exploratory analysis like a scatter diagram, and you can identify the variable to fit the model. Okay, so you can identify that. But before doing that, we need to establish the scientific relationship. For example, if you look at any simple example like the yield of certain production process may depend on the temperature, pressure, catalyst, and rate of throughput. So if you take an industrial example like that. So the production, the yield is very important, and they want to improve the yield. So, for example, yarn processing or a textile example, always they want the yield should be higher and higher and higher, because then the production is higher, then the cost is reduced, then they can get a better profit. So another important one is the speed of the spindles. But at the same time, when the speed is increased, then you can say the yield is going to increase. But what is the quality of that? So the unevenness is going to be an issue. So we need to consider that also. So different variables we need to consider. So then how do you fix this one? So we have a different variables we need to be considered for the particular response variable y. And another one is the rate of defectives of a process may depend on the speed of the production line. So how many defectives are coming? So larger and larger defectives are coming means we get speed is very important one. So speed is increase, the defectives are there. So what is the optimum one we can go? So that type of relationship is needed to make a planning purpose. And the volume of the tree, in an agricultural example, we can say related to the diameter of the tree at the first height of the tree, and the taper of the tree. So we can get different types of examples around the world. So it is very important to know in each case the scientific relationship. And the fuel efficiency, you can see that automobile, now the petrol prices is increasing, so we need to know how efficient is your car and everything, all things. So it is depending on the weight, how many cylinders are there, and the characteristics of the engine and the body. So a lot of things are going on. Apart from the individual property or individual measurements of the car or the vehicle, okay, so other parameters also important. Okay, so we need to get that relationship to see whether we can fit a better model to model the fuel efficiency or the response based on the covariate. And if you look at the employee efficiency, the HR problem, maybe also we can relate it to the performance of the employment tasks, year of training, educational background, etc. So we can also figure it out what are the different types of this one. And other one people use is the customer satisfaction, employee satisfactions also. So what are the things it is related to the other way? So the idea is once you have this relationship, then we can find out the ways to improve it. So that is why we normally use the regression modeling, and also for prediction purpose, we can use this. But the main issue here is we don't want unnecessarily variable get into our model, and which are unrelated, very difficult to explain it. So most of the time when we get some data sets and we do the analysis without understanding the process from which the data is coming, we can fit the model. But then we can give a good interpretation and everything, but it is most of the time it is meaningless. So getting out of the variables, the selection of the variable is very important in the beginning. That is also some sort of variable selection, but it's a scientific way of doing this. That is, we as a statistician cannot do much on that. You have to get the expert opinion from where the data is coming, and they can identify, oh, this is not a good variable to enter in the model. So once you identify the variable, then we can fit the model. So in all these examples that we discuss, we are interested to obtaining a model or a law of relationship among these variables. So we have a Y and different X's are there. So we want to identify a model. And it is we want to get a functional relationship between the response variable and one or more explanatory variables. So normally one means we normally call as a simple linear regression model, or then there's a single one. We don't need much variable selection. Either goes only one variable, and we can say that that variable is important, and if not important, we can only the response variable alone is good enough. But these models also, you can see that the how. And another one is if you the variable already in the model, you are assuming, then what type of relationship? Okay, how the relationship? It is a quadratic way, or is a linear way. So the scatter diagram will help. Also, sometimes it will be helpful for you if you know the scientific background, like laws of physics or chemistry or a general science. Also will tell you how these two variables are related. Okay, so like the pressure is increasing, the hardness of the this is increasing or not. So depending on the industry, we can see some information scientifically. So that will also help you to modeling the true relationship. So in some cases, we can see the constant, the mathematical function is known. So the constant, the mathematical function means sometimes the equations is known for a modeling, but that means the parametric value will be available. But most of the time, that parametric value is not available. So we need to fit this model and from the data. So once we have the data, then we can fit and see what could be the parameter. So just like in regression, normally you call the parameter beta, y equal to beta 1 plus beta naught plus beta 1 x1 plus beta 2 x2, etc. This betas are the constants what you're talking about it. So if you know the relationship, you can put the exact value from the theory. Otherwise, we have to collect the data and fit it. Though the theoretical models are absent in general, that is the main issue. But in sometimes in the science, we can always find out this parametric value. So we always depend on the fitting this model. So empirical models are needed, and how that will tell you once you fit this model, we can see the data, how the relationship is coming there. So before we go and fit this model, we have to keep in mind what Professor George Box commented in one of his lectures: all models are wrong, but some are useful. So we can find out different models, but all are not wrong because we don't know the truth, but some are useful. So you can find out the best one to suit for your purpose. So I will try to fix this problem by using the notations here. So we have the response variable y, and we have a set of covariates x1, x2, etc., xp minus 1. So p minus 1 covariates are there, and we think that this response variable is believed to be influenced by a large number of covariates. And even though we got this one based on the scientific knowledge, some of them have a very weak influence, some of them very high influence also, some have absolutely zero. So excluding those variables or covariates which have no or very weak influence, it will lead to a simpler model. So if you have 10 variables and we think that we find few of them are have a zero influence, then we come to 6, 4, or 5, then that is very easy to interpret and also have a good predictive values also. So that is what we are looking in the variable selection. So we are finding out a subset of the covariates that is simpler model leading to simpler model, and which have a better interpretive value. So it's easy to go with the simpler ones. So if you consider a simple linear regression model, G mu x beta, so mu is the mean of the model, and x is the covariate, and beta is the parameter. So we can say that this mu can be easily written as beta naught plus beta 1 x1 plus beta 2 x2 plus etc. beta p minus 1 xp minus 1. So this is the mean we can identify from this model. And if you write the normal model, we can see that y equal to this plus epsilon. Okay, so random error or the noise. So this is the average model. Okay, so y equal to x beta. So this is the one is a multiple linear regression model. But we can also consider the same thing as a generalized linear model, GLM, where the G function is again the same thing here. The linear way is written x beta. The G could be a different one. Like what you call here is a link function in the generalized linear model. For example, you can consider in the Poisson regression model where y could be 0, 1, 2, 3, etc. That is the attribute type of data, or y could be 0 or 1 category, that is the logistic regression is coming there. So there the mu function could be not just mu, that simple linear way. So it could be a function. So that link function, we make this leading to the mu, then we can do it. So whatever it may be, so the link function is there, but we have the problem here is we need to identify which are the variables are important, which are not important, and we finding out a subset of the model which is easy for us to predict. And we assume that when you're fitting this model, including all covariates is true. That is the full model, what we call is a model with all covariates, and we assume that that is the correct model. From then, we are trying to find out a subset of this model or subset of the covariate and fit the model and see whether this is almost approximating the true model, that is the full model, and which is closer. So if we're very closer to that, then we don't need to go for the full model, we can go for a sub-model. A regression model with a large number of covariates is undesirable because interpreting a large model can be difficult. So we have a large number of variables, and a large model often has a poor prediction precision. So prediction also not going to be good also. Okay, so the idea here is very clear here. So we will have a large number of covariates, and we want to find a subset of this covariate that is approximately or very close to the true one, all variables, the model, then that is our best model for that. Okay, so in this scenario, we can find out a different criteria by which we can select which is a better one. So I'll give you an example where it is the one of the complicated model here, but a high dimensional longitudinal data. Longitudinal data means, we have a response Y and we observe it over the time. For example, an individual going to a doctor's visit in a year. So then how often he's going to the doctors, all the 4 years or 5 years. So we can see every year we can get the same number, some number of visits to the doctor's office or next to 4 years or 5 years. So that is what you call the longitudinal data. That is same individual we are observing over the time. So, but not a longer one, not 200 years, because impossible. But what I'm saying is the longitudinal is not a longer time series. Okay, just 3 or 4 time points. So, and when we are modeling this, we consist of repeated responses on the large number of covariates also there. And instead of looking at a large number of covariates, but instead of that, we look at a subset of them are relevant for modeling the response variable. A model with a smaller number of covariates adequately represent the data. That means the full model also there and its relationship. So we don't want to include the redundant variable, and which may hinder the accuracy and efficiency. So we need to develop this variable selection methodology, and especially in the high dimensional case and also in the longitudinal. So this is another example, but but if I just little bit went there, that is my from the linear regression, generalized linear model, then the longitudinal. Okay, so the difficulty is coming higher and higher there. So we'll go with this variable selection methods with a simple linear regression models, which is almost extendable to any other model. Okay, so there are many methods are available in the literature. I am classifying into different groups here. So first one I'm just trying to call as the information theoretic approaches, and another one is the sequential approaches, and another one is the penalized likelihood approaches. Okay, so the information theoretic approach means this is again going to be the likelihood based and other things. So we can see using the R-square adjusted value. So we can use the one criteria for selecting the best model by looking at the R-square value, the adjusted R-square. So another one is the CP statistics, there's the Mallows CP statistics. And another group of information here is the Akaike information criteria and the Bayesian information criteria. AIC and BIC is very well known there. And we can also use the cross validation. And also there are many modified versions of the AIC, BIC. I will give you a simple idea there, but I'm not going to give you more on that today. And the sequential approaches is like forward selection criteria or backward elimination criteria. And we go with the stepwise approaches. So combination of the forward and the backward. And the other approaches is what you call the penalized likelihood approach. It is somewhat similar to the AIC, BIC, but there is a great difference also. Somewhat looking at the model, you can say it is similar, but it is slightly different. Okay, so I'm just going to look at the first two sections here, the information and sequential approaches. And most of you might have learned there, but I just want to review how it is going to be there. Then we look at more detail in the penalized approaches in the second part of my talk. Okay. So what is the R square? So, so R square is a good criteria to identify a model. So what is R square? So for example, if you say Phylum regression model and your R square is 0.85, it means that 85% of the variation in the response is explained by your model. Okay, so we have the Y variable. So we are interested in the Y variable, and we fit a regression model for the Y with a set of covariates. Then you can find out the R square. So that is when you fit a model, always you look at the testing of the betas and you look at the R square value. So R square is very, very important criteria. People use it. And again, I'm telling you, the explanation is that how much is the variability of the response variable is explained by the fitted model. So when you add one covariate or a regressor in the model, the R square will always increase. So if you have a 10 variable and you got R square is 0.8, then 11th variable is added, you will never ever get less than 0.8. So it will always increase. So in that case, if you use that as a criteria, so we cannot use that model, R square, to find out the best, because keep on adding a covariate, always the R square is increasing. So to avoid the difficulty interpreting that R square, we can use the adjusted R square. So if we have a K regression parameter, adjusted R square can be written as 1 minus sum of squares of the residual divided by n minus K minus 1. N is the sample size, K is the number of covariates minus 1. Then SST is the total sum of squares of the Y values and divided by n minus 1 observation. So you get this R square. So R square adjusted. So we can rewrite this as in terms of original R square value, which is always increased when you added the covariate. So 1 minus n minus 1 by n minus K minus 1 into 1 minus R square K. So this means it is different from the R square. So if it is really the added covariate improve this, reduce this mean square error here, then only the R square will improve, R square adjusted will improve. So if R square does not improve, n minus K minus 1 will actually lower the adjusted R square. So there is not much improvement using the new covariate value. The adjusted R square will be reduced. So we can see that if R square K plus S, is already we have a K, and you add K, additional covariate will increase the R square adjusted K if only if partial F statistics for testing the significance of the S additional regression exceeds 1. So this actually can do it. This is a testing of hypothesis going to be there. So if you add additional S covariates, the R square is increasing or not. If it's not really increasing, then adjusted R square will not increase at all. So the strategy here is to select the best submodel which have the maximum R square adjusted K. So you can calculate the R square adjusted K for all the models, and we can see if it is improving, then you can take it. So which is the maximum R square adjusted K, you can use it. Equivalently, another one also we can see the residual mean square is almost like an equivalent one, residual mean square. So we can also, when you use the regression model and you can find out the mean square of the residual for the K regressors are there, then you can find out this mean square error. So then you can also look at all possible cases here, then you can find out what is the best one. So a regressor K in terms of in the regression model will cause the MSR K plus 1 to be greater than K if it decreases the residual sum of squares. So the main thing is, if you use the R square alone, you can see that what is R square? SS residual divided by the sum of squares of the total. So the total is fixed, then residual. So if it is increasing, whenever you add a covariate, always it is getting reduced there, right? So this will be reduced. So we can get that away. So it is not a good idea to do without the denominator there, n minus k minus 1, because then it comes the mean. So k plays a role there. So plot the MS residual k versus k, and the choice of k is based on the following. Choose choice of k. So what k is better to use? The minimum of MS RS k you choose, and the minimum value of the k such that MSK is approximately equal to MS residual or the full model. So you can choose the minimum MS and also is closer to the MS residual of the full model. And the value k near to the point where the smallest MS RS k turns upward. So you can plot it and see when this smallest MSK turn upward, that point you can take it. Okay, so it is not just looking at only the smallest one. So this is one way of doing it. Then another one is the most commonly used, people use the CP statistics also. So the Mallows CP. So this is a very common one used, but it is, softwares are available, but it is not easy. Again, you need to have some criteria to do that. So the full model, if you fit, have P regressors that P plus 1 parameters, including the intercept, and let S square be the mean square error of the full model, then we assume that the full model gives adequate description, then expected value of the S square equal to sigma square. So that is their assumption. So if your S square is very close or adequately description of the full model, then you can get this one. So if you fit a submodel, now P plus 1 parameters are there, you go with the K regressors, and the adequate when this ratio, again, sum of squares of residual K divided by sigma square is approximately equal to chi square n minus k minus 1, then expected value of this is going to be n minus k plus 1. So that means the mean square error, you can see again, sum of squares of residual of k divided by n minus k minus 1 is approximately expected value is going to be sigma square, then that's going to be a good model there. So the mean square error from the submodel, this sum of squares of residual k by n minus k minus 1 is an unbiased estimate of the sigma square only if the model is adequate. Okay, otherwise this residual sum of squares of residual is much more than n minus k minus 1 sigma square. Okay, so the CK or CK we can calculate it for each one of them submodel, and the S square is an estimate based on the full model. Then you can calculate the CK for all the submodel for the full model. Okay, if the submodel is adequate, then this value should be closer to k plus 1. So that is a catch here. So we can plot this CK versus k plus 1 and draw a line with the point 0, 0 and p plus 1, p plus 1. That is the diagonal from this origin. Then we can see what value of CK closer to the line. It should be smaller and closer to the line, then that is the best submodel is going to be. So you have to understand one more thing is the k equal to 5, for example, means k covariates. There could be different k's, okay? So different models could be possible. That is 5 variable in the model, you can choose any number, any different types of covariates there. So you have to calculate for all of them. So each point, k equal to 5, you can get many. Okay, so still we have to look at the CK value closer to the line. 0, 0, and p plus 1, p plus 1. And whoever is closer to this line, and with that, the smallest value is going to be your best submodel. Okay, so it is, you need to really look at the graphical plot there. So that is why some people won't do that, because they have to go and look at it. So otherwise, most of the coding is done just calculating this and doing it. So some software is giving you the plot also, then you can use it. So, so these are the one of the important model people use, and it is, some of them are equivalent, very close to each other. So another important one is the Akai-K information criterion, known as the AIC. So in short, AIC is known, but you can write this AIC as n log sum of squares of residual k by n plus 2 into k plus 1. So this one is the n log sum of squares of the residual of the kth regression model divided by n plus 2 into k plus 1. So this portion, 2 into k plus 1, is generally known as the penalty. So how many variables are, how many covariates are in the model? So k increases, this is going to be increased. And a submodel with the smallest value of AIC is preferred. So you can see that when the k is increasing, the AIC is also increasing. Okay, so again, then depend on how this sum of squares or residual is going to play a role there. So, for example, if you have a k equal to 10, so how many models are possible? 2 power k minus 1. So that many models are there. So because the simple model can be just variable x1, then another one is x2 separately, x alone like this, then x1 and x2, x1 and x3, x1. So all possible combination has to be done, similar earlier also, and find out the AIC for all the models. Each time you find out the residual, you can see the value always in a fitted model, then you can calculate it, and you can calculate the number of variables in the model, covariates plus 1, then you can calculate the AC. And almost all software will give you the AIC value and you fit it in the regression model. So it is easy to find out this value. Only the trouble is that I think few softwares are there, but it's a little bit complicated there. So you can calculate the AIC by your own way. So if you have a model, you can, if you are good in R, you can write a simple code to choose each submodel. You can taking a subset of the model and fit the model, finding out the AIC. So a little bit programming is required if you are not using any libraries in the R, but AIC value is always calculated. So you can fit the model, and you can do this repeated for all the submodel, and you can get a string of all AIC value and find out the minimum corresponding to what model, then you can use it. So a submodel with the smallest values of the AICs are preferred in this situation. And other one is the Bayesian information criterion or Schwartz information criterion. So generally known as the BIC. This almost look like same. So this you can see the penalty part, 2 times k plus 1 was the penalty for the AIC. Now here the penalty part is k plus 1 log n. N is the sample size you use, and k is the number of variable covariates in the model. So again, the criteria is same. When you compute for BIC for all the submodels and choose the model with the smallest BIC. And you can see in the literature, very, very difficult to beat this criteria BIC. And BIC is found to be the best method among all. Okay, So, but different criteria and different scenario is going to be different, but very, very difficult to beat this PIC. So it is one of the preferred model, and it is very dependent on the K as well as the sample size. If the sample size is going to be large, here is an issue, but it's a log of n. But seems to be a more interesting one. And there are different variations of the AIC and BICs are also available. Okay, so this is the basic thing. Now you can remodel this. So this part, the AIC part, part is called as the sum of squares or residual, because here we are talking about the simple linear regression, multiple regression model. So no generalized or anything. So this could be, now you can consider the regression problem as the estimation of the fitting, assuming the errors as normally distributed. You can assume you can write down the likelihood and estimating the procedures are there. So we can write this first part as a likelihood, that is this, and second part keep same as the penalty. So then you can put instead of likelihood, you can put a minus likelihood, then penalty, then you can minimize it. Or likelihood minus penalty, you can also do that. So that is what I'm telling you, that is going to come more on the penalized likelihood part. But it can be considered as an extension of the BIC and AIC there, here. But the problem here is we have to do all possible cases and we have to do that. Okay, so this is a better method, an efficient method, and very likely difficult to beat this one. And another one people use this, the cross-validation. So R-square or R-square adjusted will give an indication how well we fit the current data. But this will not be necessarily indicative of the accuracy of the prediction of the new observation. Okay, so the problem here you have is you feeding this data for given data, but most of the time we may look at the prediction, how the model is going to predict the new observation. So in that angle, you can look at the variable selection in terms of the cross-validation. So we can get the idea of the prediction accuracy of the model from the predictive residual statistics. So the predictive error, that is how you predict this observation, okay? So can be obtained by fitting the regression model without the ith case. So if you use the same data to predict it, that won't be a good model to predict this one. So you have to remove the data and one observation or two observations, whatever it may be, then fit the remaining data and predict the new observation, so which is independent of the data you use for estimation, okay? So without the ith case and predict the ith case with the fitted model. So you can get the y hat ith observation when we use the model without the ith observation. Then we can compute the error as yi minus yi hat minus I. That is, when you use the prediction, I didn't use the ith value for that. So then you can compute the prediction error for each observation, and the cross-validated root mean square error of prediction is 1 by n summation I equal to 1 to n yi minus y hat square and take the square root. So you can find out the root mean square error of the prediction for that particular model. Then you can use this one, because we are using for all observation I equal 1 to n, but each time we remove the observation and predict it. So for each submodel you can do this, and you can choose overall all the submodel, you look at it and find out which one is getting a minimum value, and that could be your best model. Okay, so a lot of computation is required. So if you have 1,000 observation, and for a submodel, you have to fit almost 1,000 models and find out the error there. Similarly, you have to do for all submodel. Okay, so the computational part is here huge compared to the other methods. But if your idea is to use this approach or the model for the prediction, and this is one of the recommended one for this. And this one is the very commonly, I think you almost, maybe I go a little bit faster here, that the automatic methods. So automatic method is what normally called the forward selection and backward elimination and stepwise. So I just give a summary of what is a forward selection and backward. So forward selection means you start with a simple regression model. That means only one variable in the model. And the variables we are adding one by one sequentially as necessary until the final model is selected. So that is only we are looking at the forward, and we can look at the backward in the sense we fit the full model and remove the one variable, then you again remove another variable until some conditions we put it and we can fix that model. So either you go forward or come backward, or the other one is what you call the stepwise. So that means you start with a forward, select one single model and fit it and add one, and same time you look, you can delete one or not simultaneously. So until the final model is selected. Okay, so this is very easy way we can do it, and each time we can decide to add a variable or remove a variable based on the statistical procedure. Okay, statistical test can be done. If how do you select the one, and I'll explain one of them, and it can be reverse it for the backward, and you can do that. Okay, so step one in the forward selection is fit the P models, all the single covariate model, and you can choose the variable has the most significant regression coefficient. So you can choose the one of the best or more influential regression coefficient, that is the significant one, then highest significant, then we can use that as a simple one. Then we can choose, we can put a criteria, whatever alpha or whatever it may be. Okay, if that is significant, then you get into that. Then we can go with another variable. Second variable, you can add it. Then second variable also can be added, is the most significant remaining one. In the partial test we can do. Then you can keep on doing that until nothing is going to be eligible to enter in the model. The same can be reversed in the backward. So you go the full model, and the least significant you remove. Again you do the test. Then again next least one you do it. And once we cannot remove it, that is the one. And the final one, then every time you do a testing of hypothesis, there the significance of that. Okay, so the backward elimination can be done, and the stepwise means you do combinedly. It's the same time you do add one, then you think about removing the other one. So how it is going to be matter? Because sometimes what happened, even though we assuming a basic assumption here, the linear dependence is there, but some of them are linear independence is there, that is the covariance, but sometimes some correlations are there, so taking the variable out may reduce the effect of the other variable. So this model is generally look good, but it depends on many things, and it is not going to be considered all possible submodel. So then this is not a best method to do it. And the criteria is, again, testing is there, but there are methods available in the forward regression, forward selection, backward elimination, and step. Also, we can use a criteria like AIC, BIC for that. So instead of significant test you do, you can also a criteria what AIC values are there, and we can decide on based on the AIC, you can allow the variable is getting to the model. So softwares are available. I think the stepwise regression, I think step with the AIC options are available. You can use that, the one. So if you don't want to use the testing the significance as a criteria, to enter the model, enter the new variable in the model or remove the variable from the model, you can use the AIC as the criteria to use this. So that's why the AIC or BIC is very common in many places. You can use that as a criteria too. Okay, so then the next part is coming, the penalized one. I think I will go with after the break. Before that, I will go with a simple some code I can try to give you. 1 minute. I will share with another.
Hello.
Can you see my Word file with variable selection using R?
Not yet.
Huh? No.
Not yet. Yeah.
Okay, so this is the title is variable selection using R.
Nikhil?
Can you see that?
No, not yet.
Oh, sorry. Then I think I need to. What you are seeing maybe in. Okay, share. What about now?
Yes, sir. Possible, sir.
You can see that, right? The Word file?
Yeah, now it is. Yeah.
Okay. So there are in the software, the R, there are many codes are available for this, doing this. So I'm just trying to see where the one you can do with the R square, adjusted R square or malloc CP. Okay, so this is available in the library Leaps, and you can use this, download this Leaps, and you can use it. And there are there are many other libraries are available in the R, like for example, Caret. There's another one. Then so there are many. You can look at the Google and you can see, because this is the one very easy. That's why I was trying to see. And the malloc CP, if you want to use, you can also use this one. So the library Leaps you have to download, and you can use the library Leaps first, then get into the library. Then I just put some example with the data set. For example, data set, the name of the data set should be data set here. And the response may be Y, and the columns of the covariates are named as X1, X2, etc. So that is the framework you can do the data set. Then you can just put the Leaps X equal to the data set 2 to 10. So we have 10 columns. First column is the Y, and from 2 to 10 is the covariates. Then you can say what is X and what is Y. The names you can use, the method. So you can, option is there, you can use the method. The CP, if you put it, you can get the output there, Leaps, and you can find out the first one. So this is a simple one. And you know that is what is the simple one, that the other one is the REG subsets, the regression subset method. So you can see regression subset, and Y tilde X1 plus X2 etc. X10 you can put it, and you can put data set, and other ways you can use the earlier way, data set 2 to 10 or whatever, maybe you can use it. And best subset is 4, so you can get what is the numbers coming there. N-best give an option to give a number of best subset model from among all models of the same number of covariates. So you are asking for what is the best subset. 4 of them you are going to give it. Okay, so you can also get that way. In this case, we can use the plot command to possible model. Plot out scale equal to CP. So it will give you a CP plot. I told you earlier, you can so 0, 0, P plus 1, the line, then closer to the line, and this. Okay. Otherwise, other methods are easy to do it. So you can also use. So for each model, we fit using the LM function, we can find AIC or BIC in general. So in the R, the simplest one is to use the LM function, that is linear model, y tilde, x1, x2, etc. If you put it, always you can get a linear regression model, and you put a summary, you can get the summary, and AIC of the output of this variable. Here, out is the variable, okay? So you can put AIC, you can get the value. So you can get that AIC from each model. Only thing is you have to fit all possible, all AIC, all submodel, you have to fix it. So if you are a little bit, if you are good in R coding, so we can fix, put a matrix of variables, and you can select the variable for the subset. Okay, so you don't need to every time, because it's a manually you have to enter x1, x2, etc. Okay, so but if you put x equal to a matrix form, then you can put different combination of the model. Then you can select those variables from the the covariate data, then you can model it. So you can little bit do the programming here, then you can get AIC, BIC for all possible cases. Then once you fit that model, you can get AIC out, that AIC value will come, or a BIC value will come, then you can use it. Okay, so this is another one. Also, people use the trust statistics also for some finding out the one. So you DAGG library also, you need to use that. Okay, so if you want to use this step, is the function in the R, I think you can directly get it from without any other library here. Use the step means it will give you a function R to select the model using the AIC based forward, backward, or both approaches. Okay, so step out, scope equal to this, upper is full, over equal to this, direction is the forward. So direction is the one you use. So it will give you full model and to the one model. Okay, so forward way you look at it and you can get it. So you can also use full in the full model. Okay, so that is the other way of doing it. So I think this is very simple. That is why I didn't give you really an example one. So if you type this variable selection in R using step or something, always you can get a online documentation there. You can always find out that. So if you want to use the stepwise regression with the F value, we can do it using the 2 command, drop time and update, drop time out, test is equal to F. So if you can use the, instead of AIC, you can use the F statistics for testing in that. So that's a way you can use it. But what I'm suggesting is, when you use this R is, so a lot of commands are there. You should get an idea what actually the R is doing. Okay, so always find out when you go to the particular command, you try to get a help file and identify what are the things available, how you put this command, what are the options you have, then what is the output is coming, what are the values in the output. Sometimes you just put it output, only one value will come, but there are many values will be there. So you can use this the name of the output, name bracket out means you are putting the command here out, then you can see what are the values are available. Okay, for example, if you put the lead LM function here, this LM out. So this out LM, So this is a linear function model you are fitting with the y and x1, x2, etc. So this output is just what output. So sometimes we just give you a regression coefficient. So if you put a summary of the output, you get all the values. So you can put the names bracket out. You can see what values are available for the output. So so many values are available. So coefficients, regression value, R square, test statistics value, and everything. So you can use those information to do many other things there. Okay, so like out residue value also we can get it. The hat value you can get it in the regression model. So you have to understand what this function is used, what are the input value you should give, and what the output you are getting, what are the different values you can get it. So using that value, ANOVA, everything you can get it from that out. Okay, so you have to utilize that and for this. Okay, I think I will have a break, 5 minutes, then come back. Is it okay?
Okay, sir. Okay.
Yeah. Okay, is ready?
Okay. Okay.
So the screen is visible, right?
Yeah, this visible.
Okay.
Penalized
Okay.
likelihood.
Huh?
Penalized, yeah. The variable
Yeah,
select.
okay, yeah, that's okay, yeah. Okay, so so we talk about the traditional method, like a theoretic informative method and forward selection methods. So the main issue with AIC and BIC, they call for fitting all possible submodel, which is computationally expensive. So if you have a 10 variables and 2 power 10 minus 1, so that many variables has to be fit. So that many models has to be fit. So it is a tedious job. So if the number of variables are larger and larger and larger, then it is really computationally it's not efficient, very expensive. So, and the forward selections are okay, but the problem is we are not considering all possible models there. So only we look at in a forward way or backward elimination, and it's not easy there also. So it is easy, but it is not effective. So instead of that, so there are new class of methods they call the penalized likelihood approach. There are many methods are available. One is called lasso, that is based on the penalty part. Then SCAD is there, adaptive lasso, least square approximation, and folded concave penalty. So there are different methods are available. So here in this approach, what they do, the variable selection and estimation is carried out simultaneously. So there's not a submodel concept is coming there. So the estimation and variable selection is going to be parallel. So we can do easy that way. So what is the penalized least square approach when you use? The least square estimate can be by minimizing this. That's normally what you do in the regression, y minus x beta, y minus x square of that, right? So that's minimizing it. Now we can write this, the penalized least square estimate by minimizing this part plus a penalty part we introduce in this. Like, so we try to minimize, but we are adding some penalty there. And P lambda, this part, sorry, this is the absolute value, is a penalty function. We can use a different penalty function there. So now we can think about this same as AIC or BIC. So we have this first part is always there in the AIC. Then we can see the penalty. So the penalty, we can say that the 2p in the AIC and 2 log n, the one in the BIC. Sorry, not 2 log n, p plus 1 log n, right? So p log n, okay. P log n is the one there, not 2. Sorry for that. So that is the penalty. When you put it back, then we can see that is the penalized part also. So that's what I was indicating earlier. So AIC also considered as a penalized way of doing is the penalty is giving you a number of variables in the model in the AIC, and other one is p times log n. That is the penalty for the BIC. So we can also consider that way. So if you assume the distribution, now because this is a linear model, we wrote it. Now, when you write as a likelihood approach, how do you do? So you can see that the linear multiple linear regression model, we are assuming that distribution of the error is a normal distribution or assume distribution. We can use the likelihood to arrive the parameters, and if you use the normality assumption, then we can see the estimate of the parameters is exactly same as in the least square approach or the likelihood approach. Okay, so we can also use the error part there. So then instead of writing the penalized least square, we can write the penalized likelihood estimate by maximizing the likelihood minus penalty. Because earlier we have a least square, that's the minimization procedure. So we add the penalty. Now we have a likelihood that's always to be maximized. Then you minus the penalty we can put in. So the idea is the same. So here we have to maximize this likelihood. Then this maximizing the penalized likelihood is equivalent to minimizing the reverse way. Okay, you can put the minus of the likelihood plus penalty. Okay, both are the same. So we can think this AIC, BIC as the 2 into P plus 1 or P plus 1 log n respectively. So you can think about the same approach, the penalized likelihood, either maximization or the minimization problem, and it has a similar way you can also represent the AIC or BIC. Okay, so but the problem is we can use the different types of penalty here. But when we use the AIC, BIC, we use all possible regression model and finding out the minimum. That is the easiest way in that particular case. But here what we are trying to do is we have a likelihood and the penalty function and the penalized likelihood we have. Now you can utilize the standard approaches to estimate the parameter. And you can give a different penalty, P lambda, different ways. So that is why the lasso, they give a different penalty. SCAD, they give a different penalty. So you can use it. But how do you estimate the parameter? So that is, I'm not going to talk too much on that, but that is, again, you have a likelihood to be maximized or minimized. And here the the penalized likelihood. Then you have the this one, the penalized likelihood minus this penalty. So you do any method to optimize that. So you can get an estimation there. So standard, so normally what we use is take the derivative and equal to 0, then you solve the equation, then that equation you can solve. So you can use a Newton-Raphson method or modified Newton-Raphson methods. Numerically we can do, no closed form solutions will be available here. So when you use this penalty, so what is a good penalty we can give it? So the penalty, when you give, that penalty should satisfy some criteria. So one is the unbiasedness. The resulting estimator is nearly unbiased when the true unknown parameter is large to avoid unnecessary bias. So when you use this penalty and when you get the estimator, resulting estimator should be an unbiased one. Okay, when the parameter value is unknown parameter is very large. That means very large means that particular one, we should not give any penalty to that. So it should get almost equal to that same value. So the penalty should not have any effect on that. And the second property should be the sparsity. The resulting estimator is the thresholding rule, which automatically set the smaller estimator coefficients to 0 to reduce the model complexity. So if the unknown parameter is very, 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 very small, close to 0, then this penalty should push them to 0. So when this estimate of that particular covariates, the estimate regression coefficient corresponding to that is going to be 0, that way we can see that it is negligible there, 0 value is coming, so the variable selection is going to be there. Okay, and the estimator also, whatever the resulting estimator, and by this one or sparsity, whatever we're getting is continuous in the data, so to avoid the instability in the model prediction. So it should be continuous. So if you have a good penalty, which have unbiased for a higher value, should not get that value, should be smaller or no reduction or anything. And if it is very, very small, effect of that covariate means it should be estimated as 0. then that could be a penalty. So there are different penalties are available. So penalty functions of interest is hard thresholding penalty, but is normally hard. So they put the penalty as delta square my absolute value theta minus square I indicator function is less than delta. That is a hard penalty. And soft penalty, what they call the lasso. This is this one. Then the ridge regression parameter also we can see that absolute value theta square into delta is this one. And the scat penalty, that is the one shown to be better one, smoothly clipped absolute deviation penalty. And this penalty generally you can arrive it, but the derivative of that penalty only is available in the literature. So because whatever we put it, we have a penalty likelihood plus minus the penalty, and when you want to get the estimate, you have to take a derivative. So we use the derivative here, okay? So that derivative only required. So, and this derivative one is delta into this is a function is here. So this is the scat penalty. So we can use a different penalty. The penalty functions are introduced in the literature as L1, L2, and hard do not simultaneously satisfy these three mathematical conditions. What I gave you earlier: unbiased, sparsity, and continuous. And the SCAD is all possess all of them. So all the properties we wanted, the SCAD is the one have. So we can use this. So you can see that the SCAD penalty. So how this is going to be here? There, this is the P1 equal to P2.3 value if you give LP penalties, and this is the hard and SCAD. So this is going to be, otherwise it's going to be this value, the penalty P beta is given. So you can get this. So I'm not going too much detail about the properties of that, but you can use this, the penalty, different penalty assumption we can be given there, and we try to estimate the parameter of the beta. And the idea is, if the parameter is very, very important one, it should be estimated as same as the original value. And if it is not effective or not influencing much or negligible, it should force to zero. Okay. So when the true parameters have some zero components, that means their negligible coefficient covariates are there, and corresponding regression values are closer to zero. They are estimated as zero with the probability tending to 1. So almost always going to be 0, and estimate the other non-zero coefficients simultaneously. So the other non-coefficients also should get correct value. And exactly same, but if it is really the true parameter is non-zero, it should be 0, it should be 0, non-zero will be non-zero. So in order for their computational efficiency and stability, and it satisfied the oracle property, the 3 property, with the property, the choice of the tuning parameter, the lambda or delta. So you can use a different software for this one. So R, SAS or Stata, we can also use. R software is free, so there are different libraries are available. So you can also check for GLMNet, Caret, or NCPen. So these 3 softwares are available. I think now more than that also available. So you can download and you can use this penalized part very easily there. So we'll try to give an example here, a simulated example, and see whether how this would. So the performance of this need to be assessed using a large number of simulation. But here I'm just giving you one. So it may be giving you think that, oh, it's not working. But, it is the data we generate, and it may not be always representing. So we need to run this code for more than 1,000 or 100,000, then see how these parameters are estimated and the variable selection is coming correctly or not. Okay, so we consider a simple model here. Y equal to beta naught plus beta 1 Z1 plus beta 2 Z2 Z3 Z4 Z5. So we can take 5 variables here, and error term. So this is our normal model here. So I generated the data Z1, that is covariate value from 0, 1 normal, and Z2 from 1, 1, that is the average is 1 and standard deviation is 1. Z3 is 1 and 0.5, Z4 equal to binary 0.5, Z5 equal to Poisson 1.5 data. So the X's are different and different distribution. And if you really want to do a good simulation, so you can see that sometimes X1 and X2, X3 maybe have a little bit, because now they are independent. So sometimes they may have some dependencies are there. So you can use, instead of independently generating Z1, Z2, Z3, I can use a multivariate normal generation. So you can use the library for the multivariate, and you can generate it with some correlation between X1 and X2. So you can give a mu vector and you can give a covariance matrix. There we can put some correlation, covariance between X1 and X2. Otherwise, normally give 0 for independent, but you can get very small 1, 0.1, 0.2, something like that. So that will be more reliable. Okay. Then binary also we can give sometimes. Most of the variable could be 0, 1 category. So Z5 can be Poisson also. So I took a small sample size here, 50 generated sample from each, and use beta. So original beta, I can take beta equal to 1, 1, 0, 1, 1. That is, sorry, here, Z1. Sorry, I think this should be 0, okay? So Z1, Z2, I think there's a typo here. Okay, so my true model is Z1, Z3, Z5. So this corresponding covariates I can use and multiply by the Y, and you get the error, you get the Y value, and you can get X1, X2, etc. Then you can get, but my true value means Z1, Z3, Z5. Okay, so I think one is missing here. That's the issue here. So one is Z1, Z2 is equal to corresponding beta 2 equal to 0. That's correct. And Z3 is 1. I think 1, 1, 0, 1, 1, 1. Okay. So I'm just trying to Z4. Z4. Sorry, 1, 1, 0, 1, 0, 1. Okay, that's the way. So beta 4 equal to 0. That is why their model is coming here. 1 plus Z1 plus Z3 plus Z5 is coming. So corresponding to X2, Z2 and Z4, the coefficients are 0. Okay. So this could be 0. Okay, I'll make a note on that. So then error also I generated from N0, 1. So I can generate this value. So I can get the X's, multiply by the Z. Then goes beta equal to this is given. So I can use this Y can generate it by just putting Z1 plus Z2 plus Z5 and get this value. So, so this is a simple code I have here. Z1 equal to R norm 50 and Z2 equal to R norm 11 and Z3 equal to R norm 51.5. If you know the R, very easy to understand it. Z5 equal to R Poisson and C combined. Then I get the Y as 1 plus Z1 plus Z3. And Z4 and Z5 5 plus R norm 50. So this is my Y, but you can see that Z4, effect of Z4 and Z2 are not there because their corresponding coefficients are 0. Okay. Now, I do not know. So I fit the model with all the Z1, Z2, Z3, Z4, Z5. So I can use this fitting the regression model here. So I can get this summary of the fit. You fit this simple linear regression model, I can get the estimate. Now this is a good idea to look at the estimates. So is it what we model or the simulation model is getting correct or not? But in most of the time, what happened is, because we are generating a random observation, sometimes the value could go. So, for example, N01 you generating, The mean is 0, standard deviation is 1. So the range of value could be go from -3 to +3. So the data you generated in one may get an outlier, not outlier, it's from the same distribution you get. So one data generation may not be good, but it's only for a demonstration here. That is the reason I'm telling you. Okay, so we can see that this data looks generated better. You can see that Z1 is significantly, that is beta 1, testing the significance is significantly different from 0. Then Z2 is not significant, Z3 is significant, Z4 is not significant, Z5 is significant. So in the output, you can give you everything, a significant code, and these ones are given residual error. And the multiple R-square is given, adjusted R-square is given, F-statistics is given for the full model, and the p-value, everything is given. So actually, we can look at this data set and we can see that the model with the Z1, Z3, Z5 is better, but we never go with that way. So now if you want to use this, I just use one of them, NCPen. NCPen is the software I was downloaded for this purpose. You can use the other two software I mentioned earlier. GLMNet also good one software. So now the library NCPen, and I'm trying to use the SCAD penalty. So the model we can use as the NCPen. That's a command. Y and Z, the matrix is the Z and Y is the vector here. And you just put the penalty equal to SCAD. So that's the only thing you need to do. So put the penalty, the method, you are doing the SCAD, and it is automatically do the one. And the output, you can see GIC, NCPen, fit to YZ. Because the parameter we are estimating, well, there is another parameter, we have to do this GIC method, generalized information criteria they use to identify the that parameter lambda. So then you can find out what is the output of the optimum beta. You can see that intercept is this, Z1 is this, Z2 is 0, Z3 is this, Z4 equals 0, Z5 equals 5. So this automatically give you the variable selection by estimating the other variable Z2 and Z4 as 0. Okay, so this way show that the variable selection and estimation is done simultaneously. But now you see the same data, we use the LESO, that is the other method penalty, we can use it. Now we can see the Z2 is forced to be 0, but the Z4 is no. So this method, the different method will give you different results, okay? So, and this is based on the one data set. So how do you check this, the efficiency of these two methods? So you repeat this procedure 1,000 times and see whether how many times Z1 is estimated as non-zero, and Z2 is estimated non-zero, Z3 is non-zero, and all. And again, Z1 is estimated 0, Z2 is estimated 0, like that. So number of correct decisions and number of incorrect decisions also can be done for Z2 and Z4. Because it's a simulation setup, you set the data, what do you want, and giving the allowance for the noise and other things. So you can see the efficiency of the method. Then almost you can see the 100% of the time Z1 is estimated as this is correct. Then another thing you can do is you can also do the bias check. So you know the true value, but it is giving estimated as 0.67. Here is 0.97. So you can also look at the bias in the estimation. So you can find out the average value of the estimates minus the true value. You can find out the bias. And how many zeros are there, incorrect decision, non-zeros, correct zeros, these things also you can do it. So this is a one data set, we cannot do much on that, but you can do this as the, so if you have only one data set and you want to do this method, so you can do the the machine learning technique like split the data. So 80% of the data you put aside, feeding the data, testing the data, then, so 20% testing and 80% you can use as training the data. That you can repeat it many times. Then you can check how the estimates are coming and you're getting. So that the problem is the simulation. Why do you want to do simulation? In the simulation setup, we can understand what is the truth. But in the actual data, we don't know the truth. Okay, so if you don't know the truth in the actual situation, then you can do the testing and training data sets between that. Otherwise, in the simulation, always you know what is the data you are generating, what is the true parameter value. You can always compute and see whether you are getting the correct one. Okay, so this is a very popular method. Even I'm telling you this, this is a paper, the SCAD is written in the JASA, I think 2003 by Fan and Lee. So they use compare this, their proposed SCAD method with the different sets of methods, including AIC, BIC, LASSO, and so many other methods. There we can see that AIC is performing better. But the time consuming and in all possible cases, but the SCAD was comparatively better in that way. So the BIC is the better method to use. Is the best, very difficult to beat the method. Okay. So then another case I'm talking about this, the first slide I was giving you on example, longitudinal data. So here the modeling is slightly different because we have the Y1, Y2, yn for the observation for the n individual, but each individual we repeat the measurements m times, the different time points. Okay, so for the ith subject we have yi, yi1, yi2, yim. So normal case we have only one observation. Now we can see these values are correlated because you are taking from the same individual, so they are dependent. And corresponding also we have the covariate values, m into p matrix of covariate value for each one. So and in the longitudinals are very difficult to assume a particular distribution. So what normally they do, the mean and variance of the YIT, they defined by this mu IT, and variance of this equal to variance of mu T. Then in the distribution is not well defined, and most of them you cannot use the likelihood, so they can use the quasi-likelihood. So the quasi-likelihood, they assume only the two things were mean and covariance. That's it. Okay. So the quasi-likelihood estimation of beta Q of beta is the solution of the estimating equation. Summation I equal to 1 to k. K individuals are there. Xi transpose AI sigma I rho and yi minus. So this is the true covariance matrix we assume. AI is the diagonal elements of these. You take the derivative of this one, the variance is given there. So we can get this correlation matrix, but still this correlation matrix is not known. So when this problem is coming, so the one of the best method they use is the generalized estimating equation by the Liang and Seeger. This is the one of the well-cited paper. So they use the working correlation approach because we don't know the pattern between this observation within the individual. They're correlated. Okay, so they use the working correlation, and the estimation of the beta is obtained by solving the estimating equation by this form. So only thing this R inverse alpha, they assume a particular type of working correlation. So you can use this, the working correlation as the AR1 model or EQ correlation or MA1, the moving average one. So we can assume some correlation pattern, then you can use it. But the G estimate of beta is not necessarily consistent in some situations. So discussed by Crowder in 1995 and Sutardar and Das in 1999. So the Crowder is demonstrated that there may not be any solution to the correlation parameter alpha. This is misleading to the estimation of the regression parameter. Okay, so there is an issue with that. So instead of that, people suggested using the generalized quasi-likelihood, where the equation is based on the stationary lag correlation structured by this one. So sigma I, they can be a correlation matrix. It is more better in the sense, because you can see this is the lag correlation. So this is a first observation. It itself is 1. Second, 1 and 2 is a row 1, row 2, row m minus 1. So if you put AR1, it's a row 1, row square, row cube, etc. Equicorrelation means row, like that. And MA1 structure is only this coming. So you can use a different correlation, but this is a better way. You can say lag correlation. So first one to second one observation. So time is there. So people can use the same correlation with the first observation, first individual or second individual, third individual. So they put a lag correlation and they did it. So that is the approach they use for the generalized estimating equations with the quasi-likelihood. So we try to use the quasi-likelihood, and we can use the penalized part of that. So the quasi-likelihood you can write, then you can write the penalty part. So we try to use that, how it works. So you get an estimating equation, then you take a derivative of that, U beta, so you get the same estimating equation for the generalized quasi-likelihood approach for the longitudinal, then minus the penalty, derivative of the penalty there. So P dash lambda. So we just use the SCAD option here. So you can get that, okay? So you can use the same idea, but there is no package available. So you have to use your own idea, your own way to derive this quasi-likelihood and add the penalty and do that. Okay, so the same idea extended to this case, longitudinal. And I can see if you are anybody interested on this, I can send you the paper, what we published in 2016, available in the Springer book as a booklet. So this, I'm not talking about any estimation procedure here. So this is the likelihood is getting. You take the derivative and you can use a Newton-Raphson, or you can solve this equation using any approach. You can use a simplest algorithm, or any software can be used to do that. So this is an example is discussing that, and we consider the longitudinal count data, because here the data can be the continuous data or count data or binary or anything. So this is the longitudinal data with the 144 individual with the 4 years continuously they taken from 85 to 84. Then this is the number of visits to a physician by each individual during the given year. So first year, how many visits they made, second year, how many, third year, how many, fourth year, how many, by the same individual. The gender, one chronic condition of the individual, education level of the individual, and the age of the individual. So these 4 variables you can select it as a covariate. Then here this one is the statistical test to confirm the overdispersion also. Because of Poisson data, there is an overdispersion. So we use this GE approach when AR1 and gender, this is a situation we use. We can also use this penalized approach using the GE also. And GE we use with the EQC, and we use the GQL with approach. So this is the estimates are coming here. Okay, so we can also use different cases here. Okay, I think So another approach, 1 minute, I'll give you the idea here. So another set of so this is the penalized likelihood approach, the likelihood and the penalty. And in this talk, what I was talking more on the how to change this penalty part and improve your results, keeping the likelihood part same. So the likelihood, because we can also change the likelihood and keep the other one same. So some studies are done with the changing the likelihood. And I have my main research was on changing the likelihood part. So I use the empirical likelihood, where you don't know any idea about the actual distribution. So when you want to write the likelihood, you have to assume the particular distribution. So instead of that, if you assume only whatever you know, only the mean or the variance, you can write the likelihood based on empirical likelihood and how the empirical likelihood works. So if you look at the AIC, BIC, that penalty here. So my first work, what I was doing is I am changing the AIC and BIC, where instead of the actual likelihood, I write the empirical likelihood and see how it works better. So a large number of research is done on this area, and I was proposing the EAIC and EBIC, where we can use the empirical likelihood by replacing the likelihood part. And it was performing better when the distribution is unknown to you or when the distribution is misspecified. So which was extended to the penalized part. So there also, I think I did study for the GLM as well as the longitudinal data that was published in the 2 years back in the American Journal of Mathematical Sciences, where we did for the empirical likelihood for the penalized empirical likelihood for variable selection, where I was replacing this likelihood by the empirical likelihood for the longitudinal setup. So it is complicated because, you know, the estimation and computations are very complicated for the empirical likelihood. So that's another area of work is there. So people do in different ways by changing the penalty, different types of penalty, and how do you better estimates. So the others are keeping the assumption that you know the distribution. If you don't know the distribution, then you can look at the other side, like trying to write a different likelihood approaches with the empirical likelihood, and when the misspecification is coming, it can take care of that. Okay, so so that's how 2 approaches can be done there. So in summary, the variable selection leads to a simpler model, removing unnecessary variables in the model, which is easy to interpret. And standard methods computationally not efficient, like, you know, all possible cases. Then we can use the penalized likelihood approach, perform estimation and variable selection simultaneously. So that's the advantage here. So this is extended to the longitudinal studies, and this one and softwares are available to perform the analysis of this. Okay, I think I'll stop here and welcome for any questions. Sadesh.
Yes.
Okay.
Yeah, please. Questions, since he mentioned about he's waiting for questions from the audience, please.
Hello.
Yeah, Shanmugam.
Hello.
So, yeah, please.
I have a in
Yeah.
LM function, wrote BCA in our code. The function is symbol to in package or it is the own function.
Oh, no, it's breaking up.
Your voice is breaking.
Yeah, it's not
Sundaram.
clear and it's breaking up in between.
You repeat it. Yeah.
Hello. Hello, sir. Now is it
Yes.
clear?
Now it is up. You please continue. Yeah.
Yes, sir. In our code part, sir, for in LM function, you add AC and BAC. So is it a inbuilt function with any packages or a home written function?
OEGs are always available with most of the packages. So when you use the LM function, you can always find out the
function stats package.
Huh?
It's available with stats package or?
Yeah.
Oh, okay, sir. Okay. So I think it was the own return only. So I didn't use that. Thank you, sir.
Yeah, I think you look at this. I see most of the one it should be available there. The LM function available. Otherwise, the one I showed you, the leaps or something, you can always find out that.
Thank you, sir. Thank you.
Sir?
Yeah.
Sir, there are many variable selection methods available. So which one is appropriate for a particular data, sir? Because in this example itself, Lasso forcing one variable to 0. I mean, one variable beta coefficient as 0. Where SCAD forced two covariates to 0. So which one is appropriate?
Yeah, that's what I'm saying, that, when you take another data set, it will be changing to the other one. So because each penalty have a different way to do it. Okay. So overall, you have to see the three properties, the unbiasedness and the sparsity and the continuous. So that in that way, the authors of the SCAD, they're saying that claim to be the better one. So we can do only based on simulation. Okay. So this, if you have an actual data, very difficult to say which one is going to be the right one, because you don't know the true model, right? So that is why people do the simulation and claim. So very difficult to say which one is going to be work better if you do a data set. So if you want, and another thing is, if you are looking more on the prediction, then you can use the cross-validation or something like that also. Okay. So there are many, and all will give you different results. So depending on the situation, you want to just fit the model and use for that, or you want a prediction purpose, then you can choose the variable. But you better to always fit all possible cases, and you can choose, maybe 10 methods or 10 methods you use, and which method giving you similar results. Maybe you can choose that way. One method will not give you. So all models are wrong. Some of the useful to you.
Thank you, sir.
So otherwise, there's need only one model, right? So one method to do that. So if you keep on changing the penalty function in the R, for the NC pen or what GLM-net, you can get different approaches also there. So if you look at the authors, always they claim that their method is always better, right? So anyway, you have to see that, simulations and everything, they try to understand the approach.
Sir, then how will come to the conclusion, sir? Which model is best for real data?
Yeah, that's what most of the time people do take 2-3 models. Okay, 2-3 models they identify, and how it fits and how the predictions are going on. Not a single model will not be always better. So that is why one of the soft I showed you, what is the best 4 submodel to be. So you can fit this model, and even though you do the penalization and everything, and based on that 4 model, you can fit the model and see what is the R square and what is the, then you can have a comparison also, R square adjusted and everything. So those estimates will be penalized actually, So in the penalized, in the end, you get that estimate, then you can write, then you can do the residual analysis. All other model building has to be done on that.
Yes, sir. Thank you.
Okay.
If anyone can ask one more, 5 more minutes are there. If needed, we can for the next speaker to move to the next speaker. If anyone has to add any comments or any other clarifications needed, please.
So if there's no other question, thanks for attending this workshop, and I think it is maybe useful to you some point of time. Okay. So if anybody need any copies of the slide or anything, just send me an email at, I will post it, I'll type it in the chat, variat@man.ca. So you can ask a question related to this or something else, or anything, you can always contact me. Okay, or contact Satish and he will give the information to you.
Yeah. Surely.
Okay.
Sure.
Okay. And thank you.
Okay, thank you, Professor Ashokan, for your nice talk, very informative in fact, to the young researchers. And we are, on behalf of the Department of Statistics, University of Kerala and the School of Physical and Mathematical Sciences, we would like to extend our gratitude to you, Professor Variat, for your support to our activities. Now let us move to the next speaker. Without as he mentioned, you can, in case of any help from our side, we are ready to extend. And also nowadays you can contact via email and get clarifications if you have any further clarifications requests. And let us move to the next talk. Next, our Professor Josa is here. Neha, please introduce Josa and invite him for the next talk.
Okay, sir. Now I invite Dr. K.K. Jose, Director of School of Mathematics and Statistics and School of Data Analytics at Mahatma Gandhi University, Kottayam, to speak on the topic TX family of distributions and their applications. He was a first rank holder in MSc Statistics in 1980 in University of Kerala. He was awarded PhD in Statistics by the University of Kerala under the guidance of Dr. R.N. Pillai in 1995. Professor Jose was the Associate Professor
and later the head of Department of Statistics at St. Thomas College, Palla. He retired as principal of St. Thomas College on 31st March 2014 and was holding the charge of professor and head in the Department of Statistics at the Central University of Rajasthan during 2014-15. He is presently the coordinator of Curriculum Committee for PG programs in Mathematics, Statistics and Data Science and also a member of Expert Committee for MSc Biostatistics in MG University, Kottayam. Dr. Jose has rendered more than 40 years of meritorious service as a reputed principal, professor, and head of department, teacher, and an organizer. His areas of research include statistical modeling, stochastic process, time series modeling, distribution theory, industrial quality, microarray modeling, and epidemiology, etc. Dr. Jose reputed national and international journals. Dr. Jose is an elected member of the International Statistical Institute, Netherlands, and a fellow of the Royal Statistical Society, UK. In 2022, the Indian Society for Probability and Statistics conferred him as ISPS Fellow in recognition of his contributions to probability, statistics, and related areas. It's an honor and privilege for us, sir, to have you here with us today. Once again, I invite Dr. K.K. Jose for the presentation. Over to you, sir.
Welcome, sir.
Okay, thank you. Thank you very much, Professor Sadish Kumar, and for providing this opportunity to interact with research scholars all over the world. So I will be sharing my slide. I think it is visible. Is it visible? Hello?
Yeah, it is.
Okay, okay. So, as the title is concerned, the talk is based on Gumbel-X family of distributions and their applications. And so as far as an introduction, as far as probability distributions are concerned, so for a statistician, for modeling real-life problems, real-life data, probability distributions are vital and fundamental. And we are concerned with this for creating the basis and foundation for the study of uncertainty. A probability distribution is used to better understand a data set. Probability distribution is used almost in every discipline. The generation of new families of continuous distributions has recently been of great interest to researchers. Several non-continuous distributions as well as discrete distributions are found to be special cases of such new distributions. The main aim of generating these families is to make selection of models for a given set of data easy, which are preferable to or which are comparatively preferable to other models. So statistical distributions play an important role in parametric inference and are commonly applied to model real-life data. In practical situations, existing standard distributions do not provide good fit or are not adequate to model real data sets. So statisticians are developing many new distributions which are flexible than standard distributions for the analysis of real data sets. So new distributions are developed either by combining two or more existing distributions, something like mixtures or confounded compound distributions, or by adding extra parameters to the existing distributions. And some of the works in this area are by Eugene, so who developed and studied a new class of distributions generated from beta family, beta distributions. Some of the examples are beta Gumbel distribution by Nadaraja and Coates, beta Fresher distribution by Nadaraja and Gupta, then beta variable distribution by Amoy et al. 2005, beta exponential distribution by Nadaraja and Coates, beta gamma distributions by Kong et al. 2007, beta Pareto distribution by Akinsete et al. 2008, beta generalized exponential distribution by Barreto Sousa et al. And so on. Another extension is actually that by Jones 2009, Cordero and De Castro 2011, and they are using Kumaraswamy distribution. Some examples of Kumaraswamy G distributions are Kumaraswamy Weibull distribution, Kumaraswamy Gumbel distribution, and so on. So now we will be coming to TX family of distributions, which were recently introduced by Alsatre et al. 2013. And this is actually a modification of beta generated family. As far as beta generated family is concerned, for beta generated family and Kumaraswamy G family of distributions, the support is actually in the interval 0 to 1. Whereas Alsatre's work is concerned, he is providing flexibility. So Alsatre proposed a general method by replacing the beta PDF with any non-negative continuous random variable t as the generator and applying a function u of fx which satisfies the following conditions. So here u of fx actually belongs to the closed interval a to b. Then u of fx that is having support a to b, and u of fx is differentiable and monotonically non-decreasing. And the third condition is, u of fx tends to a, that is the lower limit, as x tends to minus infinity. And u of fx tends to b as x tends to plus infinity. So with these conditions, he introduces the new class of distributions, that is the TX family of distributions, as Gx equal to integral from a to u of fx, rt dt, which is equal to a function of r of u of fx, where capital R, rt is the CDF, and small rt, that is the PDF of a random variable capital T. Here the CDF is a composite function of say this R, U, and F. Actually, so we are having R, U as well as F. So for defining the CDF. And the corresponding PDF is having a compact expression, that is a closed form expression Gx is equal to, so we can write that as derivative d by dx of u of fx into r of u of fx, that is given by 2. Then as far as Alsatre is concerned, he is giving different choices. So different choices of u of fx depending upon the support of the random variable t. So 3 possibilities are given, so which actually accounts for all the possibilities. So the first one, that is when t is having bounded support, that is in the interval 0 to 1. In this case, u of fx can be taken as fx or some accelerated function, that is f raised to alpha. This leads to the beta generated family of distributions. So beta generated family of distribution is becoming a special case of this Alsatre's paper. When the support of t is from 0 to infinity, that is positive support, where a greater than or equal to 0, so we can assume that a equal to 0. So u of fx can be defined as minus log of 1 minus fx, or something like the odds ratio fx by 1 minus fx, or minus log of 1 minus f raised to alpha x, or f raised to alpha x by 1 minus f raised to alpha x, where alpha is greater than 0. So that is our the support 0 to infinity, that is positive support. Now when the support is from minus infinity to plus infinity, so u of or logarithm of the Watts function fx by 1 minus fx, or logarithm of minus log of 1 minus f raised to alpha x, or logarithm of the Watts function of the accelerated densities, that is f raised to alpha by 1 minus f raised to alpha. So these are actually the three support bases. So first one on 0 to 1, so directly fx or f raised to alpha. The second one over 0 to infinity, where you are actually more concerned with the logarithmic functions, logarithm of 1 minus fx, fx by 1 minus fx, etc. Then the third one is actually over the interval, over the support minus infinity to plus infinity, where you are having logarithm of minus log. So now, many papers have appeared in this area in reputed journals. Gamma Pareto distribution in 2012, T geometric distribution, T geometric family in 2012, Weibull Pareto distribution 2013, exponentiated TX family of distributions 2013, T normal family of distributions 2014, logistic X family of distributions 2015, and many other papers, very recent papers are also there. So now we will be concentrating, as an illustration, we will be concentrating on Gumbel X family of distributions. Al-Aktash 2013 and Al-Aktash 2014-2015 proposed the Gumbel X family by taking T as the Gumbel random variable, with the CDF given by exponential e raised to minus of e raised to minus of t minus mu by sigma. And its density is given by RT mu sigma. So that is the PDF. Then we are considering fx, the CDF, then f bar x, that is 1 minus fx, the survival function, depending on a parameter vector theta. So the upper limit u of fx is replaced by logarithm of fx by f bar x and RT with the Gumbel density. Then we define the CDF of the Gumbel X family by, or we obtain the CDF of the Gumbel X family as having a general structure of the form gx equal to e raised to minus of, that is exponential, minus of e raised to mu by sigma into fx by f bar x whole raised to minus 1 by sigma. So for any fx, that is actually the speciality. So the PDF, also you can give some closed form expression for the PDF. So gx equal to e raised to mu by sigma, then fx, then and so on. That is actually given by the expression 6. So the support of the random variable, you can see that for the new function, that is gx, new PDF gx, is the same as that for the original PDF fx. And we can have this lemma. So let x have a density of the forms given by 6. Then the random variable t equal to logarithm of fx by f bar x has a Gumbel distribution denoted by Gumbel mu sigma. And the converse is also true. Then if t has a Gumbel distribution of this form, then the random variable x equal to f inverse of e raised to t 1 plus or e raised to t divided by 1 plus e raised to t has a Gumbel X distribution with the density given by 6. So that actually is a if and only if condition. You know, for simplicity, we start with the Gumbel uniform distribution. If the parent distribution is uniform over the interval a to b, then you know the PDF is fx equal to 1 by b minus a for a less than x less than b, and the cumulative distribution function fx is equal to x minus a by b minus a, and the survival function is f bar x equal to b minus x by b minus a. Then the Gumbel uniform density is having the structure given by 7, that is the distribution function is e raised to minus of e raised to mu by sigma into x minus a by b minus x whole raised to minus 1 by sigma. And the PDF also has closed form expression given by 8 here. Then we can consider the properties. The survival function is given, very simple expression is there given by 9. Then we have the hazard rate function, then the cumulative hazard rate function given by 10 and 11. Now we will be coming to the something on this. So if u follows uniform distribution over the interval a to b, then if you take the inverse function, that is x equal to a plus b, etc., so that will follow Gumbel uniform. over the interval, so over the Gumbel uniform over the interval A to B itself. So we have fx, so the proof is given only that much. So here RT, that is actually the same as U, and T you can obtain very easily as minus sigma logarithm of minus log of U plus mu actually. So we will be getting the quantile function, median, etc. from this. So the quantile function has the form xp equal to a plus b raised to mu minus logarithm of p raised to minus sigma whole divided by 1 plus e raised to mu minus logarithm of p raised to minus 1 minus sigma. And if U has a uniform distribution over the interval 0 to 1, then you can write x equal to q of U has a Gumbel uniform distribution. So for median, you put p equal to 0.5, then we will be getting the expression for the median, and that is here. And suppose some specific distributions you want. So Gumbel uniform 2, 5, 0, 5 and p equal to 0.5, then you can obtain the median x 0.5, so which is median x. So you can compute that to be equal to 4.894 and so on. So what I have shown is actually, so it is very easy to obtain the quantiles from here. So measures of skewness and kurtosis. As far as the skewness kurtosis coefficients are concerned, the usual moments we cannot obtain in closed form expressions, but we can make use of some non-parametric approach actually. So that is actually the measure of skewness given by Galton in 1883. So that is S of Q 6 by 8 or 3 by 4, then minus 2 Q 1 by 2, then plus Q 1 by 4 divided by Q 3 by 4 minus Q 1 by 4. So that is actually the first quartile, second quartile, that is actually making use of the first quartile, second quartile and the third quartile. Second quartile is the median itself, so that we can obtain the measure of skewness from here. And the measure of kurtosis also we can have by Moore's 1988. So there also we have this expression given by K, given by 14 actually. Q of 7 by 8 minus Q of 5 by 8 plus Q of 3 by 8 minus Q of 1 by 8 whole divided by Q of 6 by 8. 6 by 8 means 2 by 4, that is 3 by 4 minus Q of 1 by 4. So using this, we can obtain the kurtosis measure also. So that is actually something which is a parametric approach, non-parametric approach. Anyway, we can compute the values of the mean, variance, skewness, kurtosis, etc. for given for specific values. So which will give you some idea regarding the skewness. So the skewness value is 2, 6, kurtosis is 6, even that can be equal to 1.26, and even that can be equal to 0.0 minus 0.32 and so on. So as far as the values are concerned, we can have skewness to be positive, negative, all those cases, and kurtosis also of that form. These are the shapes of the density functions. So different types of density functions we can obtain, different shapes we can obtain. Then coming to shapes of the Hazard function. So the Hazard function can be increasing, decreasing, then it could be bathtub shaped and so on. So all these possibilities can be obtained from this with respect to different parameter values. And we can think of Shannon entropy. So Shannon entropy also can be obtained very easily in a closed form expression. Then maximal likelihood estimation. So if you want to find the estimator, so you can make use of various methods here. The maximal likelihood method has been used, and we are using R software also. And using that, we can obtain R software, actually the LVFGSB method. So that is actually made use of. And using this maximal likelihood procedure and R program, R code, you can obtain the parameters, or you can conduct simulations and you can obtain the estimates, and the bias values are obtained, and the mean square estimates are obtained, and so on. And we can see that as the number increases, the bias decreases actually. Now another data set is used, ozone data set is used, and we are actually, so this is actually a data taken from Nadaraja 2007, a paper which appeared. The data sets are daily ozone measurements. And for that, we have fitted the model and we have obtained the maximal likelihood estimators. We have considered the Gumbel uniform and the Gumbel-Lomax, and Gumbel uniform, the p-value is obtained as 0.8996, whereas Gumbel-Lomax, the value is obtained as 0.0067. So there is a very high improvement. As far as, hello, you can see? Okay. As far as hello, you can hear?
Okay.
Okay, no problem, no problem.
Sir, it is not clear. Not.
Maybe some.
You have to restart the presentation. That's
I have to restart, so it is not visible.
Presentation. Stop sharing.
What happened?
Started.
I think
Maybe technical issues. Yeah.
okay.
Just stop sharing and.
Now it is coming.
Yeah.
So it may be because of
Yeah.
this.
Now
Now it is okay. So
It's okay.
maybe because of our network problems. Okay.
Yeah.
So the Kolmogorov similar statistics also you can see some advantage 0.0531, whereas for the Gumbel-Lomax it is 0.15. Then Anderson statistic 0.29, and whereas for Gumbel-Lomax it is 11 point, and so on. Then Kramer-Von-Mises is also. We are having very good improvement with respect to the Gumbel uniform distribution with respect to this data set. And this PP plot, QQ plot, etc. we have made use of. Then we will be coming to some acceptance sampling plan. Place the plot down.
Again, same problem, sir.
Again, some network problem is coming. I don't
Yeah,
know. What
probably the weak network.
Maybe, however, it is Asianet. Anyway.
Okay.
Anyway, or may I think.
If it is, it's better to stop sharing and
Once again,
start it.
enter. Oh, that
Once again.
I will think of.
Yeah. Hi, Professor Filippo. You are also there in the group. Professor hello.
Okay, sir.
Yeah. Professor Filippo in between. Yeah, in the time.
Let me see. Oh, I have to open it.
Let us wait. No problem, sir. Please. Just start.
So
share.
some
Yeah.
some problem.
Technically, yeah.
Okay.
Yeah, now it is coming. Yeah.
It is coming.
But again, the same. Yeah.
I think some problem due to network. No, it is not.
Whether we need to share from here, sir.
Okay, you can think of that.
You can share from here and you can speak from there. If there is difficulty, till there is difficulty.
I will just. Problem. Let me check whether it is with the connection or something.
Yeah, let us try once again. Otherwise, just send a mail to.
Okay, sir.
My Nikhil is here. He will help you.
Surely.
Yeah.
I don't know why it is. Here it is open.
Okay. It's mainly because of the network issue, probably. I think so.
Maybe it has been working well.
Whether you have chosen the entire screen or not?
It's coming anyway.
Yeah. It's better to use the entire screen.
I was using the entire screen actually.
Okay. Even then, okay.
Let me see. Let me try once again.
Yeah.
Now it is coming. Now it is coming. Okay.
Yeah. Okay. Now it is fine. Yeah.
So now we will be coming to acceptance sampling plan. As far as acceptance sampling plans are concerned, it is an inspection procedure used to determine whether to accept or reject a specific quantity of material. It is applied to a series of lots. It prescribes a procedure that will give a specified probability of accepting lots of given quality. It is an inspection based on qualitative measurements. In acceptance sampling inspection, a defective article is defined as one that fails to conform to specifications in one or more quality characteristics. A common procedure in acceptance sampling is to consider each submitted lot of products separately and to base the decision on acceptance or rejection of the lot on the evidence of one or more samples chosen at random from the lot. If good products are rejected by sample information, the risk involved is called producer's risk. Whereas if the bad products are accepted by the consumer, the corresponding risk is called consumer's risk. A decision to accept or reject the lot is subjected to the risk associated with the two types of errors. The procedure is statistically termed as acceptance sampling based on life tests or reliability test plans. Let the reliability test plan for accepting or rejecting a lot where the lifetime of the product follows Gumbel uniform distribution. So we assume the lifetime to be following Gumbel uniform distribution. In a life testing experiment, the procedure is to terminate the test by a predetermined time t and not the number of failures. If the number of failures at the end of time t does not exceed a given number c, called the acceptance number, then we accept the lot with a given probability of at least p. If the number of failures exceeds c before t, then the test is terminated and the lot is rejected. For such truncated life tests and the associated decision rule, we are interested in obtaining the smallest sample size. So we need the optimum sample size, that is smallest sample size to arrive at a decision when the sample size itself. So to getting larger sample size is a costly problem actually. So in many cases, in industrial context, it is a costly problem. So our life testing experiments are more concerned with smallest sample size. So here we are having the Gumbel uniform distribution. Then here the average lifetime depends only on theta, and if mu and sigma are known, so let theta not be the required minimum average lifetime. Then this is like the condition, the Gumbel uniform with respect to theta, that is always less than or equal to the distribution function. So for theta greater than or equal to theta naught. A sampling plan is specified by the following quantities: the number of units, n on test, the acceptance number c, the maximum test duration t, and the minimum average lifetime represented by theta naught. So these are the four quantities which we are more concerned in sampling plan or test plan. So the consumer's risk, the probability of accepting a bad lot should not exceed the value 1 minus p star, where p star is a lower bound for the probability that a lot of true value theta below theta naught is rejected by the sampling plan. For fixed p star, the sampling plan is characterized by n c t by theta naught, By considering sufficiently large loads, so you can make use of the binomial distribution, binomial approximation. Binomial distribution can be used to find the acceptance probability. The problem is to determine the smallest positive integer n for given values of c and t by theta naught such that LP naught, that is the LP naught that is equal to sigma I equal to 0 to c NCI P0 raised to I 1 minus P0 raised to n minus I in such a way that it is less than or equal to the designated value 1 minus P star. So here P0, that is actually that for the minimum, so that is actually GT mu sigma 0 theta naught. That was actually given earlier. And the function, so you consider the OC function also. The OC function, that is LP, is called the operating characteristic function of the sampling plan. And if the acceptance so the average lifetime of the product is increasing with the theta, and then the failure probability P theta decreases, implying that the operating characteristic function is increasing in theta. And the minimum values of n satisfying these are obtained for some specific values for illustration. Mu equal to 1, sigma equal to 1, P star equal to 0.75, 0.90, 0.95, 0.99, and so on. And the results are given in table 1. Then after that, we will be considering some Poisson approximation also. So that is actually when your P value, the P naught is very small and n is very large. Then in which case binomial tends to Poisson. So the Poisson approximation can also be used. So we will give this is the expression for the operating characteristic function OC. LP is equal to sigma I equal to 0 to c NCI P0 raised to I 1 minus P0 raised to n minus I. Then we will be finding C from table. So this table is giving the different values of C for different levels. That is P star equal to 0.75, 0.90. Only two values are exhibited here. So with respect to that, so T by theta 0 is considered. So certainly theta 0 is something which is fixed. So T is actually, so 1.5 and so on. So C values you will be getting. And the minimum sample size, that is actually 10, 20, etc. These values in the table will give you the minimum sample size, which will ensure that probability. Then 0.95, 0.99, all these values are actually. So this table actually gives you some idea about the optimal or the smallest sample sizes. Then the minimum sample size using Poisson approximation. In the case of Poisson approximation, a little more improvement is there, but it is possible it can be applied only when the probability is very small and n is very large. Then we can consider the operating characteristic function that will explain the performance. So the probability values are here. So in many cases you will be you need a very high value, that is 0.99, etc. For that you have to devise your experiment in such a way that, and so suppose your n is equal to 24 and P star equal to 0.75. So correspondingly we will be getting for possible values. So theta by theta naught equal to say 2, you are getting the probability, the OC function having value equal to 0.99 and so on. So that you can ensure. So from this you can adjust, or you can devise your machines in such a way that these values are obtained. Then so the same is continued for P star equal to 0.95, 0.99 and so on. So I shall explain the application. So this is actually with respect to some illustration, with respect to some software data. So ordered failure times of the release of a software given in terms of hours from starting of the execution of the software up to the time at which a failure of the software is occurred. This is taken from Wood's book 1996. So these are the values 254, 788, 1094, 54 and so on. So the average lifetime, let the required average lifetime be 1000 hours and the testing time be 750 hours. This leads to a ratio T by theta naught. So T by theta naught, T is actually 750 divided by theta naught is 1000. So 0.750. That is actually the value for T by theta naught. with a corresponding sample size n equal to 9 and an acceptance number c equal to 2, we will be getting p star equal to 0.75. Therefore, the sampling plan for the above sample data is, so the sampling plan is specifying these numbers n equal to 9, c equal to 2, t by theta not equal to 0.750. So we accept the product only if the number of failures before 750 hours is less than or equal to 2. So that is actually how we execute the program. We will accept the product only if the number of failures before 750 hours. So we will be waiting for 750 hours. And if the number is less than or equal to 2, then only we say the product meets the specifications. However, the confidence level is assured by the sampling plan only if the given lifetimes follow Gumbel uniform distribution. In order to confirm that the given sample is generated by lifetimes following the Gumbel uniform distribution, we have compared the sample quantiles and the corresponding population quantiles and found a satisfactory agreement. Certainly, you have to examine whether your data fits Gumbel uniform distribution. And as far as so that we have compared and we have got satisfactory agreement, so the adoption of the decision rule for the sampling plan seems to be justified. So that is actually the way in which we will be proceeding. So here we will be considering, say, the Marshall-Olkin family of distributions. Marshall-Olkin family of distributions. So now we are actually going to extend the model the further. So Marshall and Olkin in 1997 introduced a new method of adding a parameter into a family of distributions. This is a paper which appeared in Biometrica. According to them, if G bar X denotes the survival or reliability function of a continuous random variable X, then the addition of a new parameter results in another survival function S bar X alpha, given by S bar equal to alpha G bar divided by 1 minus alpha bar G bar X, where alpha bar is just 1 minus alpha. And here this alpha can be any positive value, where alpha greater than 0, X could be any value between minus infinity and plus infinity. The random variable is real valued or positive valued as the case. In all such cases, this is valid actually. Then we are applying that to the Gumbel uniform distribution, so that we will be getting the new family called Marshall-Olkin extended Gumbel uniform distribution. So here, so if you apply the transformation, the Marshall-Olkin transformation, then we will be getting G bar X equal to, so you have G bar X equal to 1 minus e raised to minus lambda fx by f bar X raised to minus 1 by sigma. And if you apply that, then you will be getting the new Marshall-Olkin Gumbel family as Marshall-Olkin Gumbel uniform family as having survival function as Sx alpha equal to alpha into 1 minus e raised to exponential minus lambda fx by f bar X raised to minus 1 by sigma whole divided by 1 minus alpha bar into this expression. So that is given by 24. So this gives the general form. Now you can make use of any suitable fx. So that is actually, suppose you consider uniform over 0 theta. So any uniform distribution you can fit here. You can substitute here. So if x follows uniform 0 theta, then f bar X is 1 minus x by theta. And the distribution function is CDF is fx equal to x by theta. So if you substitute, you will be getting the survival function given by 25, then the CDF given by 26, and the PDF also is having a closed form expression. So that is given by 27. So this way, we will be getting the PDF of the Marshall-Olkin Gumbel uniform distribution. And here the uniform distribution is defined over the interval 0 theta with the support 0 theta. Then we have the different shapes of the density function. Then the hazard function also having different shapes for different possible values of the parameters. Then quantile function also can be directly easily obtained. And if you are specifically considering, say, uniform over 0, 1, then the random variable you can obtain. And in that case, you can get the median for x equal to 0.5. And the measure of skewness, etc., you can obtain. Very close to form expressions can be obtained easily. Now, so we are considering geometric minimum as well as geometric maximum. So here we consider sequence xi be a sequence of IAED random variables with the common survival function G bar X. So you assume a geometric random variable n which is distributed or independent of sequence xi such that probability n equal to n is p into 1 minus p raised to n minus 1 for n equal to 1, 2, 3, etc. And un is actually minimum over xi, then un is distributed as Marshall-Rödkin-Gumbel uniform if and only if xi follows Gumbel uniform. So here your n, that is minimum over this, and the other case, so you consider the maximum also somewhat the same situation you will be getting. So maximum for, so Vn equal to maximum for 1 less than or I less than, so sorry, this small n, it is actually capital N. So probability maximum of xi, that will be distributed as Marshall-Rödkin-Gumbel uniform 1 by p. So instead of p, it is becoming 1 by p, lambda, sigma, theta, if and only if xi follows Gumbel uniform. So both are actually in the same. So that is known as geometric extreme stability actually. So estimation of parameters in the new form also. So we have considered the estimation of parameters using the maximum likelihood method, and we have obtained the estimates. Certainly the computation becomes complicated. Certainly we can make use of our program for evaluating. And we are applying that to a real data set. The data set is on breaking stress of carbon fibers, and that is actually taken from the book by Nicholas and Padgett 2006. So the values are given and we have obtained the estimates, and as far as the values are concerned, so we can see that the Kolmogorov-Smirnov value for the Marshall-Rödkin-Gumbel uniform is actually 0.0738, whereas for the Gumbel uniform it is 0.12, and the p value is 0.6459. For the Gumbel uniform it is 0.07. So there is very high improvement, 10 times improvement actually. So the PP plot is given here, then the estimated PDFs and so on. So here also we are considering some autoregressive time series modeling. So this is actually the Marshall-Rödkin family of distributions are actually feasible, are helping in autoregressive time series modeling, especially in the case of minification processes and maxification process. So autoregressive model is a stochastic process, as you know, used in statistical modeling in which future values are forecast based on a weighted sum of past values. An autoregressive process operates under the premise that past values have an effect on current values. Here we discuss various autoregressive models of order 1, namely Marshall-Rödkin-Gumbel uniform with the marginals, namely the minimum min process, maximum process, max min process, and so on. So this is the structure of the first one. This is called a minification process, a minification autoregressive model of order 1 with the Marshall-Rödkin-Gumbel uniform stationary marginal distribution. So here Xn is having this structure. So Xn has two components. One is epsilon n, that is the innovation structure, innovation with the probability delta. Minimum of Xn minus 1, epsilon n with the probability 1 minus delta. So in this case, this innovation, epsilon n is having a significant role. So something like rainfall, something like some booms due to some policies, etc. Some war happens, then there will be some sudden changes. So having this probability. So in many places we are experiencing heavy rains. So in such situations, so usually in Bangalore this year, and some years back in Chennai, some years back in Mumbai, etc. We are having this type of extreme climates. So in that case, epsilon is having some significant probability. So that is actually the situation in which this type of models can be used. And this can be suitably defined using Marshall-Rödkin-Gumbel uniform marginal distribution. And another, and here this is actually the result. I am avoiding the proof. So the sequence section is stationary Markovian with Marshall-Rödkin-Gumbel uniform distribution with the parameter delta, lambda, sigma, theta, if and only if sequence epsilon n is distributed as Gumbel uniform. Then even if the proof is there, I am avoiding the proof. Anybody who is interested, he can refer the slides. I will share the slides. If X naught has an arbitrary distribution, even if the distribution is arbitrary, the model remains the same, then the minification process is asymptotically stationary with the Marshall-Rödkin-Gumbel uniform. So that is also provided by this type of models. And the proof is here. Then now we are considering a model in which this xn minus 1, the process value is having some significance irrespective of epsilon n. So process value xn minus 1, then epsilon n, then a combination of both minimum of xn minus 1 and epsilon n. So in such a situation, so some example you can think of as the river flow rates, etc. So in our usual Indian rivers are concerned, especially some rivers are dry during part of the year. For about 3-4 months, the river is actually dry. So in such a case, there is no stream flow at all. So in such situations, you can have this type of models. So xn minus 1, epsilon n, minimum of xn minus 1, epsilon n. So in such a case, this type of models can be used. So this type of models, you can think of something in terms of finance case also, financial modeling also. So suppose xn minus 1, xn depends on xn minus 1. There is no extraneous factors. Something like a dull market you can think of. Then epsilon n, when some policy changes are made, there is significant effect. Otherwise, minimum of xn minus 1, epsilon n. So such situations you can make use of this type of models. Another possibility is actually here also the result is given in the form of a statement like theorem. So the sequence section is stationary Markovian with Marshall-Gumbel uniform distribution with the parameters tau, lambda, sigma, and theta, if and only if sequence epsilon is distributed as Gumbel uniform with the parameters lambda, sigma, and theta, where the tau is actually delta 2 by 1 minus delta 1. Then we can think of other possibility, that is one way maximum, another is minimum, and xn minus 1. These are the three components. There also we can define the process, and that is also feasible with this Marshall-Gumbel uniform distribution. Then that is given in the form of a result. This process, this AR1 process, maximum process, maximum as well as minimum are there. So this is called maximum process with the Marshall-Gumbel uniform distribution with the parameters lambda, tau, sigma, and theta, if and only if sequence epsilon is distributed as Gumbel uniform, where tau is actually delta 1 by delta 2. Some conditions are there actually. So the proof is here. Then all the four components, maximum, minimum, epsilon n, xn minus 1, all the four components are playing here. And in that case, we have a very general model, and there also this model can be made use of. So that is actually the peculiarity of this type of models. These Marshall-Akin processors are feasible to this type of this type of processes. So that is also of use actually. So the proof is given here, and the statement is given in the form of a theorem, so that here tau becomes delta 1 plus delta 3 by delta 2 plus delta 3. These probabilities are having some importance. The proof is given. So sample path, we have obtained the sample path. The sample path is, that means that is actually usually in the course of stochastic processes. We examine the sample path, how flexible it is. So as far as the first model, the first sample path is concerned, it is significantly different from the second one. Then some other possibilities are also here. So once again, some problem has come.
Yeah.
That is actually because of this, I think, networking problem. So now it is a very heavy traffic is there, I think.
Okay.
Let us wait. I think it is coming.
Stop sharing and repeat. So
Once again, I will stop sharing and I will try. think it is coming. Okay. It's fine. So here also, so you are having different types of sample paths. Now we are coming to stress strength analysis. So as far as stress and strength are concerned, so here we consider the random variable y representing the stress and x representing the strength. So we are of interest, when will the system work? So R equal to probability x greater than y, that is strength greater than stress, then only the system will work. So that R actually represents some efficiency of the process, or if R is, this R is actually measuring the stress strength, that is actually how stress is overcoming, strength is overcoming stress. So here y is the stress and x is the strength. So if stress and strength, this R exceeds, if stress exceeds strength, the component or the system would fail and vice versa. So Gupta et al. 2010 defined the reliability measure for Marshall-Rifkin extended distribution, and we can obtain this R is equal to probability x greater than y. We can simplify, and that is equal to alpha by alpha minus 1 square into minus log alpha plus alpha minus 1. So where alpha is actually equal to alpha 1 divided by alpha 2. So that is actually the intensity. So alpha is equal to alpha 1 by alpha 2. So this alpha 1 and alpha 2 are referred to as tilt parameters. So this is actually having applications in biostatistics, in dose response studies, etc. So when you are developing medicines, so this alpha 1 and alpha 2. So you can compare the efficiencies of two drugs. So in such situations, the first one is having alpha 1 as the parameter, tilt parameter. For the second one, alpha 2 as the parameter. Then this R is actually expressing the efficiency of the first over the second, you can think. So that way, we can define stress strength reliability, or you can obtain the expression, and we will be getting, say, Kx, that is actually, let us consider the PDF of the Marshall-Rifkin-Gumbel uniform, and we are going with the log linear function. Then you are estimating the parameters. Then you are trying to estimate, you are conducting a simulation study to obtain the average wise of the estimate of R, the average mean square, the average length of the asymptotic 95% confidence interval, all those. The coverage probability of the n simulated confidence intervals are given here. And that is actually here average bias, average MSE, and so on. So this way, we can obtain, you can examine the performance and the average confidence length and coverage probability of 95% simulated confidence intervals is given by here actually. So different values of M and N, and then we will be getting the coverage probability is actually very close to 0.99, 0.98, and so on. So in a similar manner, you can proceed. So here we are considering Pareto distribution. That is actually a model suitable in the case of income, wealth distribution, etc. So that way, we are having the Pareto distribution with density function equal to, or survival function as 1 minus x by theta raised to minus k, or f bar x equal to x by theta raised to minus k. So that way, you will be getting the survival function, and you can obtain the Gumbel uniform. And if you substitute, you will be getting the Gumbel Pareto distribution. So shapes of the density function you can study, and shape of hazard rate function also, the behavior you can study using the derivatives, and that is given here. So anyway, I'm more interested in some other things. Water statistics. So if you come to water statistics, there also we can make use of this, and we can apply that to water statistics. Then the maximum likelihood estimators are considered. Then we are applying that to some data on what you can say successive failure times for air conditioning system. So, and this is actually a data taken from Proshen 1963. And there also we can obtain very good values for the KS statistic, as well as the KK information criterion, BIC criterion, and so on. So the Gumbel-Pareto model suits this data. Another is actually the ozone data, which we have already taken, and there also we are having somewhat good performance with respect to this one. So the Kolmogorov statistic, KK information criterion, etc. are comparatively good as far as Gumbel-Pareto model is concerned. So this way we can consider different types of models, and there are also stress strength reliabilities considered actually. Then we can come to some other applications. This is actually explanation of that. So Fresher distribution that is used for extreme value cases, and there also we can obtain similar results actually. I am not describing all this. Gumbel-Fresher distribution we can define, then the properties are studied, mixture representations you can obtain, quantile function you can obtain, incomplete moments. In this case, we are considering incomplete moments, and the incomplete moment, the incomplete moment is defined as phi st equal to integral 0 to t x raised to s gx dx, and that can be computed, and certainly some very nice closed form expressions are not available. Anyway, we are having this expression, and that you can tabulate. Then probability weighted moments you can consider. So there you are actually multiplying by a probability density function. So rho rs is equal to expectation of x raised to r into gx to the power s. So that you will be getting the expression this way. That also helps you in some cases. Mean deviation you can obtain. Then Bonferroni and Lorentz curves you can obtain. Application of these equations can be made to obtain Bonferroni curve as well as Lorentz curve. So in many cases, this Lorentz curve is actually a measure of inequality. In this case also you can make use of that, and that will give you something regarding variation. So that is also a graphical procedure for studying variability, and Bonferroni index also can be used. Moments of residual and reversed residual lifetimes. So that also you can obtain. So the reversed residual lifetimes, that is the moments, we can obtain m and t as 1 by 1 minus gt integral t to infinity x minus t raised to n dgx and so on, and that you can have closed form expressions. However, the computation may be a bit difficult since you are having incomplete gamma functions, but tables are available actually. So reverse residual life we can compute, that is m and t equal to 1 by gt of integral 0 to t minus x raised to n dgx, and that also you can obtain in terms of incomplete gamma function, and that you can tabulate. And moment motion Renyi entropy also you can obtain. Delta entropy, that is actually a generalization of Renyi entropy, something which is connecting Renyi entropy with the Shannon entropy actually. Then applications are done with respect to survival lifetimes. So this is 64 observations of survival times of injected guinea pigs with different doses of tuberculosis bacilli. And there also we have the Kolmogorov-Smirnov statistic is 0.0784 compared to the Weibull-Frechet 0.18 and so on. The p-value if you consider, that is 0.8327 compared to the Weibull-Frechet, it is having 0.0328 as the p-value. So the Gumbel-Frechet model is far better compared to the Weibull-Frechet model for this data on lifetimes. Then we are considering transmutate. So what is actually transmutant? So transmutation is actually something like a modification here. So the CDF of the transmuted model, and we are considering such things. And properties are considered. So a physical interpretation of the transmuted Gumbel-Pareto model is possible if you take a system consisting of two independent components functioning independently at a given time. So if the components are connected in parallel, the overall system will have transmuted Gumbel-Pareto CDF with alpha equal to -1 and so on. And another motivation for the transmuted Gumbel-Pareto distribution follows taking two IID variables, say Z1 and Z2 with the CDF, then Z12, which is equal to minimum of Z1, Z2, and Z22, that is maximum of Z1, Z2. And if you consider X equal to Z12 with the probability 1 plus alpha by 2 and Z22 with the probability 1 minus alpha by 2, then the CDF you can obtain, and that is having this expression given by 74, and that actually gives you some idea regarding the transmuted Gumbel-Pareto and its hazard function and so on. And there are also some mixture representations that are possible. Quantitative functions can be easily obtained. Moment generating functions, incomplete moments, mean deviation, Bonferroni and Lorentz curves. All these measures you can obtain. Mean residual life functions you can obtain. Reverse residual life function you can obtain. And parameters can be estimated using maximum likelihood estimator as well as the employing the R program. And here also we are considering fitting the data to the model to a data set consisting of Gogolens taken from Kundu and Rakav's paper. And there we are having, and we are comparing this to fit the exponentiated transmuted generalized Rayleigh distribution with the transmuted variable Pareto distribution. And what we have observed is here the AIC values we have, then the log likelihood values and so on, and they actually give superiority to the transmuted Gumbel-Pareto model. So the PP plot is given and so on. So these are actually the references. So now it is time for questions actually. Hello, sorry, sir.
Yes, sir. Yes, sir. Yes. Yeah. If anyone needs any clarifications, please.
Kalyanan sir is there. Sir?
Yeah. If need someone or two, we can allow one or two. Yeah. Someone.
Oh. There is one person.
Kalyanam sir is trying to say something.
Rasool.
Good evening, sir. Sir, actually, I am a research scholar pursuing the research in the same area on which you have elaborated this session, sir.
Oh.
Sir, my question is actually sometimes when we do the analysis part on the application data sets, like you have, sir, 2-3 data sets. Sir, is it necessary that for all the data sets we need to compute the p-value, or we can check the superiority of the model by just computing the AIC, BIC, and log likelihood function?
Actually, all these are actually different measures, different methods. So in some cases, the Kolmogorov-Smirnov value may be giving a good, a better indication, but p-value may be good. That will give you something regarding the probability of its validity. It's a probability for observing such a value. So p-value, suppose p-value is very, very small, then it is not of, it is improbable, you can say. It is having less chance. So that is actually, so Anderson statistic, that also gives you something regarding the possible deviation. So if you, so in some cases, log likelihood values are considered. So just one or two may not be sufficient actually to get. So that is why we have considered different measures, only that much.
Thank you so much, sir.
Thanks, Josh, for a nice presentation.
Sir. Thank you very much. Thank you very much. Actually, it was Professor
I just want to say things are moving very nicely. And of late, I came across a particular distribution by name beta exponentiated Weibull distribution. And,
So some such works are there actually.
I came across a distribution where it's something concerned with health. They had only few data points, around 6 or 7 points. And the distribution contained about 6 parameters. And how does it matter if I can estimate the parameters using these small number of observations?
When
Computer
when
is
we
there,
are
all the 6 parameters are immediately obtained. But how far we can believe that? Is there any study relating the number of parameters and the data that is required for that? Definitely there will be some computation which will be linear within that.
Okay.
So naturally
Actually-
there will be lots of degrees of freedom. So any suggestion, anything that you have come across?
Some usually, as you know, in time series analysis, we consider parsimony actually. So we will look for those in time series analysis, time series modeling, etc. We look for parsimony actually. So the model having only less number of parameters is preferred actually. So same thing is actually there with the distributions also. When you are increasing parameters, the number of parameters, certainly there could be some sacrifice in the case of efficiency. That is actually in the case of, so everywhere you will be losing some sort of in the estimation procedure. So if 2 parameters are estimated and some approximations are made, so such a sacrifice you have to make. So certainly it is always better to have less number of parameters, certainly, surely. But so if you want to model a particular data set, in that case, it may be good. So we cannot advise for every, as a general rule, for a particular data set. So certainly if you have a few more parameters, certainly for modeling that data set alone, that may be good. That is actually what is accepted, I think.
Okay, thanks.
It cannot be.
Problem. Let me see.
So actually, I am very much indebted to Professor Kalyanaraman. He was actually the person who taught me how to compute. So actually, during my PhD works.
Okay.
So thank you, sir. Thank you, sir, for your comments.
I attended completely. No, not just post it and I was sitting, just hearing. That's all. Right. Yes.
So, any more questions?
Good evening, sir. Myself, Vidya, research scholar, Department of Statistics, Bharatiya University. Sir, I have one general question. Can I ask?
Yes, surely.
Sir, you used different kinds of distribution for unimodal data sets. What kind of distribution we can use for a multimodal and bimodal data sets?
Bimodal. Sin?
Yes. Yes, sir.
Certainly, we have to think of some other models. So when you are having bimodal, otherwise, what you can do is, in the case of bimodal, so this can be applied actually. So in such situations, we need actually some transformations, etc. Then only we can proceed. So that problem is there. So Kalyanaraman are maybe having some ideas.
In this case, what that student can do is to think of mixture of distributions.
Yes, sir.
You can just alpha 1 F1 plus alpha 2 F2. Different with different set of parameters. Like actually, this we have done long back with kind of 2 normal distributions. We can make a mixture and then do it. Quite likely, possibly you will get it.
Something like alpha 1 F1x plus alpha 2 F2x and so on.
Sir, finite mixture model. Yes, sir. Okay, sir. Thank you so much, sir. And another basic question is, basic doubt, sir, I have, which is, I worked on Pareto distribution, but the AAC value is not, I can't be calculated that because the AAC value is given by the R software is infinity. Basically,
it's not clear. It's not clear.
Actually, I worked on Pareto distribution, sir. when I calculate AAC for that distribution, I get only the answer was infinity. The answer only I get infinity only.
Or
There is no
maybe
option to get AAC value for Pareto distribution.
maybe inadequate or something, some inadequacy with the data set, or it may not be suitable actually. That may be some situation.
Okay.
So even
Actually, I worked on a lot of data sets, sir, but I don't know why it's occurring infinity. Okay, sir.
maybe some inconsistency actually.
Okay,
That
sir.
is what I can say. Yeah.
Okay, thank you so much, sir.
Actually, I have one more question. I came across with this situation, sir, where we mostly deal with the existing transformation techniques,
Oh.
like power transformation, transmuted. So many existing techniques are there. Sir, actually, I want to know how to generate a new technique. If we have to develop a new technique to develop the new probability model, how can we do that?
So that is actually, so even Marshall case, all these are actually, so we have to try with the different sets, different types of models actually, that is needed. So the best way is actually to make use of some recent papers. So start with some recent papers rather than go with very old papers. So Sadish sir may be having some good advice. So nowadays it is, in this era of data science, it is very easy, I think.
In fact, there are a lot of models, distributional models are recently coming up. We can go through those models and find which model is suitable. While considering the bivariate, one Vidya mentioned about the bimodal and multimodal distribution. There are several such models, especially in the asymmetric normal and other types. Even the Pareto level also there. I think
Thank you
you
so
can,
much.
yeah. You can go through the recent papers. That's better. There are
Thank
several
you.
papers coming out from our department also. You can go through them. Okay.
Thank you, sir.
Yeah.
Thank you so much.
So for students, my advice is research is not very difficult. So certainly something which you think to be very silly thing, that may be useful actually. So many students underestimate their capability. That is actually what I have been observing. So they don't know.
Exactly.
So they don't know the value of their work. Certainly, so you try. So nowadays you are having all such opportunities for computation, easy for getting papers, even from websites, even from Google and other surveys, etc. You will be getting research papers, new research papers. You can contact them very easily. You can contact. So in a single email, you will be getting lots of papers, or by a single search, you will be getting lots of papers. So study well and start with simple things. Work out. So usually, so you have to use your algebra, your brain. Then certainly, it is easy.
Exactly. In fact, my suggestion to or advice, in fact, to the youngsters, young researchers, is that recently there is a trend that most of the young researchers are not attending the talks, especially the invited talks and other talks in the conferences. They are just coming up and presenting their work and they go back, or they are not seriously attending the talks. So these are the platforms, and there are a lot of platforms, the opportunities nowadays. We can listen those talks from your home, from your where you are sitting. Even you don't want to go long way, because these types of online conferences, etc., are helping you. So try to tomorrow onwards we have the international conference. There is tightly scheduled several talks, invited talks, and also more than 150 contributory presentations are there. More than 100, around 100, invited talks are there. So you sit and watch those talks. And several different problems can solve. These types of doubts you can clear through the interactions. In fact, earlier these computational aspects are quite difficult. In our department, our Kalyanandan sir initiated this computational works in the statistics. In fact, that aspects. And nowadays, every researcher are doing without such computational works, they can't able to publish the works, or they can't able to say anything about or highlight the importance of their works. So I request the youngsters to please attend all the sessions without fail and utilize at your best maximum. Utilize. And I think Kalyanandan sir and Joseph will add something more.
Thank you. Thank you very much.
Now, anyone, if anyone requires to ask anything else, please. Now itself we are a little bit late. Okay. Now I think 8:20 is right time. No problem. Now let us conclude this session. If there is no questions remains, or no one is there to come forward to ask any or to clarify their doubts. Okay, let us give a big clap to the speaker, Josar, for this.
Thank you very much.
Yes,
thank you very much for
provided a lot of references. A lot of things are there. We can utilize such matters for your further research, and several things are there. And on behalf of the University of Kerala, we would like to extend our gratitude to you, sir, for your support to our activities. Thank you so much, sir. Thank you. We expect your continued support and blessings in future, in coming days also.
So thank you, Professor.
Is there any...
Thank you, Professor Satish, for providing this opportunity. Thank you for the nice listening and your interactions. Thank you. Thank you, Kalyanandan sir.
Kalyanandan sir? Yeah, probably there is some network is stuck. That camera is stuck more. Okay, let us.
Yes. My mic was muted, that's all.
Right. Okay, Professor. Okay, sir.
So the workshop has come to a very grand finale, and very congratulations to Satish for arranging 6 wonderful lectures. Not one lecture was all the 6 lectures turned out to be a very valuable lecture, and can be appreciated to any extent. And let us keep the momentum continue forever, always. All the best wishes. Thank you.
Thank you so much.
Thank you.
Thank you so much.
Thank you. Thank you.
Thank you.
Thank you, sir.